Okay, good. Good afternoon. Today, we will introduce or we will get started with deep learning, both the fundamentals and deep learning applied in the domain of image data. So we'll get started with, you could call it the computer vision part of the course, but contrary to more traditional techniques there, we will jump straight into deep learning based approaches. And what's also going to be a topic for today that we'll end with is I will introduce assignment number 2 to you guys. More information will follow on that later today or tonight about what exactly you will have to do, but I will also be introduced. And of course, as was already mentioned, assignment number 2 is going to be something that will have to do or will be around the topic of image classification as well. First of all, what's been new? After DeepSeek, there has been another Chinese company that has come out with an AI that everybody is talking about, which they call Manus AI, which itself is kind of a combination of ideas that we have seen previously, reasoning models, chain of thought, a model that has access to tools so it can do its own kind of research, quote unquote, on the web, if you will, but where they have chosen to be way more aggressive in terms of not just using the reasoning for the model to kind of self-prompt itself and then waiting for the user to give feedback again, but to have these kind of chains of thought processes to be much longer, in such a sense that they at least claim that they come or that they are reaching something which is very close in terms of being autonomous, where you only start with an initial prompt, and then the thing is aggressive enough basically to prompt itself and aggressive enough to open a web browser and to browse around and to use the different tools. They have some interesting use cases. It's not available yet for general use, so we'll kind of see how much of this stays after they have made this available. But there are some interesting use cases that they post, such as let's say performing some sort of data analysis where we want to participate in a Kaggle machine learning competition, and the only thing that we provide is a URL, and then everything else you need to do. So you need to download, you need to create Python scripts. So here it goes, it's opening a command line, it's making a to-do list of stuff that it has to do. So it has access to all of these tools, right? It can open a web browser. So it's working its way through all of this. It's acquiring the data, it's analyzing the data, it's installing scikit-learn, it's working its way through this. So it's not stopping from time to time to really wait for feedback of the user. It's just making a whole kind of plan itself and executing that plan and kind of guiding itself in that sense. And it's quite autonomous and powerful in the sense of access to tooling that this thing has. So yeah, pretty impressive, right? This is basically doing assignment number 1 in the time span of a couple of minutes, something that probably takes us a little bit more time, right? So goes to show that once this will be available for general usage, pretty curious to see how it will work in practice and what it can do. But that's Manus AI, so don't be surprised if you hear this name from time to time. A lot of news outlets have been talking about this, and you will probably hear this being mentioned a couple of times more. What's also pretty interesting, this is also a new type of model. This is something called Mercury, and this model is kind of a movement away from the transformer-based architecture that people have been using so far to train large language models, which, as you probably know, it's kind of based on the idea that based on an input sequence, the goal is that you try to predict the most likely next token, and you just sample from that. Diffusion is the approach that's being taken by, or was mainly taken so far by image and video generation models, where the idea is that you start with a bunch of random noise, and then you teach a model to take away the noise until you end up with a believable image. Later on, we will take a look probably at how these diffusion models work. The idea here is that, or starts from the basic premise of, well, if you have this kind of transformer-based approach for language and you use this diffusion-based approach for images, why wouldn't you use a similar diffusion-based approach for text as well, where you start with kind of something that looks incorrect and a complete random mess of text tokens, but by iteratively refining that and removing the noise, that you also end up with the correct end result. And so that's something that Inception Labs has been trying. They're not the first to try that. Of course, if you have diffusion models for images, it's only logical that someone would think about applying this for text as well. But there were like a couple of key issues there that weren't easy to resolve, and Inception now claims that they have managed to do that. Benefits in terms of accuracy, maybe not the best models. I mean, it comes close to GPT-4o mini, so that's not all too bad, but they claim that the output speed, so the number of tokens that you can generate per second, is way higher, making perhaps this style of models better suited for real-time applications and things like that. So what's particularly interesting, although it's like one result, we again will need to see if this is, or if others can confirm this with their own models and how easy it is to train these things. But this does kind of show that there is not only like one solution to build these LLM style models, which were transformer based models, but there is also like another approach that seems to be viable as well, at least. So that's also pretty cool to see. What else? This is something called Meshpad, where, as you guys know, I'm generally pretty interested in this kind of mesh generation style of models as well. This is the latest one in a long series of applications, and it's again, basically the idea is here that it's again doing way better than what the previous models could do. This starts with a sketch, as you see there on the left-hand side, and it basically generates a well-constructed 3D mesh out of that, and then you can make adaptations, you can make changes, you can make refinements, and the things that you get out of there, I mean, it's low poly, this is not like super high detailed style modeling yet, but yeah, imagine that you're in some kind of asset creation pipeline for like a simplistic game that you're trying to make. This is of course, or at least to me, this is a way friendlier way of working than having to open up Blender and start 3D modeling things like this directly. The paper can also be found on the webpage that you see there. Also pretty interesting is Microsoft is continuing to work on their line of small open source language models, and in their case they call that the Phi family. So just as you have like Llama from the Meta family and Qwen and so on, still Microsoft is working on their Phi family as well, which, yeah, again, is not too bad. This is mainly a series of small models so that you can run even on more or less commodity hardware. And what's new with the latest 5.4 style of models that they have released is that they are multimodal as well, meaning that in their prompt, they do not just look at text and generate text, but you can also stick in images in the prompt as well and ask them to analyze an image that you have or describe an image that you have. So that's their 5.4 multimodal model. You can put in speech, vision, and text processing now in a single architecture with only 5.6 billion parameters, which is very little, in fact. So this is something, again, if you're looking for something that you plan to use locally, you don't want to pay for an API, but you do need some kind of multimodality where you can analyze speech or where you can upload a picture to be analyzed, then this is something which is open source, or the weights are open at least, and you can download that and run that on your own devices. So it's again nice to see that we see more and more kind of attempts still in this space, and that we get more and more stronger, smaller models here as well. This is an interesting paper. If you kind of have been looking at these in the news articles and you're kind of wondering, okay, nice, all these reasoning models that we hear about, like this DeepSeek stuff and so on, these mechanisms that I sometimes mention, like chain of thought, we'll discuss some of them later on. But so far we have seen lots of different ways how you can take a language model and refine it further. And typically this refinement is what people refer to as post-training refinement, where the basic idea is, okay, you start with some kind of foundation model where you just dump in a whole lot of text that you found on the internet, and you basically just ask it to predict the next word after having given it an input sentence. But typically afterwards there follow some additional steps as well. Like now you have learned a model what language is, right? But then another thing that you will probably have it to do is align it better in such a way that it adheres better to prompts that it's being asked. So instruct tuning is typically an important post-training step that also has to be done. Once you've done that, well, it's not because now you have a model that kind of acts like a chatbot that it's always given or giving the right responses either, right? So another important step that was typically, or still is typically done, is some form of reinforcement learning from human feedback, where you try to give it some examples, and you try to teach the model, well, if the user asks how to make a bomb, probably the best answer is not just to go ahead and tell the user how to do that, but is to say, I don't want you to tell this because I don't want to inform you how to make bombs and things like that. So there is like a whole lot of this post-refinement stuff that happens here as well. And there are different ways how you can do that. There are different ways how you can make them better aligned. There are different ways how you can reach like more reasoning capabilities so that they can kind of prompt themselves and think amongst themselves. So what are the techniques that are being utilized to do this? What's the kind of the whole toolbox that we have? This paper tries to summarize all of that and put that into kind of a taxonomy or an overview, which I think is pretty interesting and a nice paper to kind of read through to get like up to date with, or a good starting idea of, okay, how do these models now work? If people talk about reinforcement learning from human feedback, or they talk about GRPO or TRPO or chain of thought or tree of thought, what is beam search and so on in this context. What is knowledge distillation, which is also something that people utilize a lot nowadays. This tries to make some sense of this all. And then finally, but this is for fun, when Andrew or Andrej Karpathy launches a tweet, then people listen because, well, this is a prominent figure in the space of AI, so every time he says something, people, of course, take notice. And now he has basically said that there is kind of an idea of, hey, have you guys noticed that nowadays if you do like recreational programming or you're like coding, that the way how we utilize LLMs nowadays is we describe our problem and code rolls out and it doesn't work, so we just copy-paste the error message and we then copy-paste the results. So and we are not really thinking anymore. We're just like the middleman for the LLM and the code editor, basically, and he describes it as vibe coding, basically. And of course, journalists and news outlets have then picked up on this, and they have been asking people like, do you still understand the code that you write? So they have been going to computer science students, and they say, well, no, we use LLMs, and we don't look at the code anymore. We're kind of like vibe coding, right? And oh no, what we will do later, and no one understands code anymore. Also fun. It's probably not that bad. Sometimes it can be fun to vibe code a little bit, right? And if it's just for throwaway projects, like Karpathy says, it's also not too bad to take this sort of approach, right? So, okay, that's it for this week. As always, these links will be posted, so you can kind of go back to them should you want to. Now, with that being said, today we start with deep learning ourselves. We start with the very basics, so we will not immediately go like a transformer model yet. Today we focus on the foundations and we focus on early deep learning attempts, you could say. Well, they're still being utilized in the image domain, early because they're mainly convolutional neural network based, whereas nowadays you have like also alternative approaches like vision transformers and conv mixers and patch based approaches, but we'll start with kind of the basics. And these will be sufficient, or the things that we'll see today will be sufficient to kind of get an idea on how to tackle assignment number 2 as well. So let's take a look. So if you have heard about deep learning, you will no doubt have heard previously that it is based on the whole kind of basic underlying notion or idea of artificial neural networks, right? So artificial meaning, well, they are not a real neural network because that's what inside our brain. Although companies, there is a company that has recently, they have been working on this for quite some time, and their idea is that they are trying to put human neural cells on a computer chip, right? And then you can train that chip by giving it electrical impulses to do something like control a robot or play a game. Big problem with our neural cells is that if you take them outside of the context of our brain, they die off very quickly because they don't like to be outside of the brain. They get infected very easily. So you need to pump them full with antibiotics and stuff like that, and you need to make sure that the fluid around them has the right composition. But they have been working on this for quite a while. I think it's Cortical Labs, if I'm not mistaken, an Australian company. And now they are like planning to release like a device where you really have human neural cells on a chip that you can train, right? So then it's not really an artificial neural network, then it's really a biological neural network. It's not scary stuff, right? You can just buy rat cells of neurons and human neurons online, right? If you have the money, these things exist. Anyway, this is artificial. So here the idea is that we do try to mimic or try to approach how neuron cells work inside of our brain from a more mathematical style of modeling. And that's, don't overthink this, right? This sounds very fancy, but the way how we will model these cells is actually quite limited by a very simplistic construct, right? It sounds very cool to do this. The basic idea is that we will have connections, right? So that's the main thing that is inspired by the way how our brain works, is that you start with a cell which is basically very simple. it can just kind of send a small voltage, but by connecting multiple cells together, that some complexity arises from that, and who knows, right? Maybe even consciousness arises from that. So that's kind of the inspirational source, nothing more than that. If you would look at how the human brain actually works, we have different style of cells. The way how we layer them together is differently. The way how they send signals is differently, because typically they work in a sort of a spiking setup where artificial neural networks do not. We will use backpropagation to train our artificial neural networks. The brain does not use backpropagation. So do not think like this is a real, we're coming close to a human or a mathematical kind of simulation of the human brain. This is not it, right? People have built simulations of a brain. I think there is like a small rainworm that has been fully modeled in terms of a mathematical simulation with like a couple of 10,000 neurons. This is definitely not, the goal here is definitely not to do that. It's just kind of inspired by the human brain, nothing more than that. What we have also seen is that if you look at tabular data, that these techniques that we have discussed, especially tree-based ensemble models, that they do quite well. Right? If you look at Kaggle competitions, if you look at real life, for the tabular data domain, all of the techniques that we have been seeing previously, they perform well. And especially things like CatBoost, XGBoost, LightGBM, they always win, right? Which is also the reason why we don't look at that many other kind of classification techniques like support vector machines or naive Bayes and so on, because we don't really need to. We know there more or less what the best models are to utilize. You could then wonder, well, why don't we also apply artificial neural networks if they are so much better in that domain? Is because for the majority of time at least, people have found that it's not worthwhile or not worthy to apply deep learning techniques in these simple, shallow cases. The performance will not be better. You will spend a longer time of training or fine-tuning or hyperparameter optimization. Of course, you will end up with a model which is totally black box, so way less interpretable, so it's probably not worth it. And in the time domain or with time series analyses, we have seen that where people have said, well, simple statistical techniques in the majority of cases, they tend to work pretty well. In the tabular domain, there have been some early papers that say, we have tried to apply a transformer-based model on a tabular set of data, and we proved that we can do better than XGBoost. No, you can't. You didn't tune XGBoost, or you cheated in some way, was found to be incorrect, right? For recommender systems, quite the same. For recommender system, basically simple techniques, they tend to work well. Deep learning techniques, they sound very fancy, but in the end of the day, it's also just like a tabular matrix of ratings of movies between user to movie, so also doesn't work that much better. That still goes for the majority of cases, but this year I should start to be a little bit careful with that sentence. And it's a little bit scary to admit, but maybe even the end is near for good friends XGBoost, LightGBM, CatBoost. I'm not sure, but there has been a couple of things that have happened recently. Thing one that has happened is in the time-based domain, we have seen the arrival of time series foundation models. Quite similar as what we've seen for text, for language, that there are people who have taken all the time series data sets that they could find online, and they've stuck them in a kind of a pre-trained transformer, and they show that in some cases that thing tends to do well. Not in all cases, it depends, and of course there is always like the question of, yeah, but is the reason that this thing then does well on your data set, is it not just simply the fact that it has seen a data set during training that looks very similar to your data set? On the other hand, is that really a problem, right? Most of the things that we do as humans are pretty similar, right? We don't invent a new word every day or a new style of time series every day, so maybe that's not really an issue. And if it would be an issue, maybe statistical techniques would break down as well at that point. So for time series, we have seen some foundation models for time series that are actually starting to do a relatively good job and who are deep learning or which are deep learning inspired. Similarly for recommender systems, if you live in the age of things like TikTok, for instance, and you look at the papers that ByteDance has published and the approaches that they take to recommend videos to their users, yeah, it's also very much deep learning oriented. So also there you see them, well, maybe there is some words or some value in using these deeper techniques as well. But okay, at least we have good old-fashioned tabular data, right, where you can just use LightGBM or XGBoost or CatBoost, and you don't need to utilize deep learning or an artificial neural network. Well, here too, we have had some foundation models for tabular data, things like TabNet and things like that, and things like TabPFM. And it was always found that, Sebastian Raschka has been keeping track since 2022 of these approaches that were never kind of proven to work well for tabular data. A couple of months ago, version 2 of TabPFN 2 was released, which is the last paper that you see mentioned here, right? So it's github.com prior labs TabPFM. Again, they redid their whole benchmark, and they do show that now for a majority of cases that they tested on, that they are actually able to beat the tree-based ensemble-based techniques. I've tried it myself in a couple of contexts for a couple of use cases, and indeed I've also found that in a lot of cases it's able to do better than the tree-based ensemble techniques can. Consider it perhaps for assignment number 1. It doesn't like to be trained on more than 10,000 instances, however, but you can force it to. And you probably will have to have a pretty beefy machine, preferably with a GPU, to train such a model on it. And again, if it then does better, you can have the discussion, is this about maybe just saw the data set before during its training process, because same idea here, these authors just took all the tabular data sets that they could find online and used them to pre-train a foundation model, but it does start to work. So we'll see what happens next with this. So not going to oversell tree-based ensemble techniques anymore. However, for the majority of cases, if you look at how much better the accuracy is for TabPFN, if you look at how much longer that it takes to train such a model, if you look at how much harder it is to then explain it to someone else, you have had a session with Shapley values and so on. You can apply that on a technique like this as well, obviously, because it's a model agnostic interpretability technique, but still it will be relatively harder to maintain a model like this to explain it. So of course there are some trade-offs to make there, but yeah, maybe we in the future will see like a complete shift or paradigm shift away from these like more traditional techniques to everything with deep learning. Who knows, right? But in any case, especially for like if your data becomes more rich and complex, think video, audio, imagery, there the claim becomes stronger to say, okay, for this maybe you need techniques that are even stronger, hence you need deep learning techniques. Artificial neural networks themselves, they have been around for a long time. And even the idea that, hey, if we can connect 2 layers with one another with artificial neurons, of course it's not so hard to kind of imagine, well, what about 3 layers? What about 4 layers? What about 5 layers? So the idea to make these things deeper was also an idea that people had for quite some amount of time, since the 1960s as well. But of course was not, or at that time was not viable because people simply did not have the compute power to do so, so to train these deeper networks. And the second thing that they lacked is, as we will see, if you make neural network architectures deeper, that this will hamper training in some way as well, which they also had to, or they didn't really knew how to solve at the time. Now, today we have better computing power. We have GPUs, graphical processing units, and tensor processing units, and neural processing units, as AMD is calling them nowadays. We have cloud computing and so on. So we have better compute power. We have more data sets, larger data sets. We have good software libraries that help us to design these architectures, and perhaps we have new use cases as well. So if you make the traditional comparison, or the comparison between traditional algorithms and deep learning, yeah, it's not just accuracy, right? But you also will need to consider training time, data requirements, feature engineering. Is it better to do that manually, or you don't want to do that manually and you let a model do that? How much hyperparameters do you have that you need to tune? With deep learning, there can be many hyperparameters that you can pick, as we will see. So it's not just always that whenever you are dealing with non-tabular data that deep learning is the best answer. There are these different trade-offs to make. Now, things are progressing as always. Yeah, training time depends a little bit, right? It says for deep learning, medium to long, but that's basically if you plan to train a model from scratch yourself. If you take a pre-trained model from Hugging Face somewhere and just want to utilize that or fine-tune that a little bit, maybe the training time is not so large overall, right? So this is kind of the overall kind of assessment, but of course, there are like exceptions to the rule. In terms of history, like I said, this has been going on for quite a while already. But don't think too much of this. Now, what is the case is that from the advent of computing, people have been dreaming about a computer that could be intelligent, right? And early cases of this, like the most famous case, or things like the Turing test with Alan Turing, right? Very famously, who was dreaming of what would it be or what would it mean for a machine to be intelligent, and who also came up with the very famous Turing test, right? How do we test whether a machine is intelligent? At the time, quite simple. You put a machine in a room and a human in a room, and then you invite some participants and you let them chat with the human over a computer interface, a textual interface, and then you let them chat with the computer for a bit. And if at the end of the session they can't tell you who was the machine and who was the human, then you can claim that the machine is as intelligent as a human. Nowadays, if you put ChatGPT behind a computer interface and you let it interface with people, a lot of people will not be able to tell the difference. So do we have true intelligence? Well, no. Of course, there have been tens or dozens of adaptations of this Turing test where people are now saying, well, but text is just text, right? It should also be about vision and images, and it should be able to talk and understand. And today, the next frontier is basically like, we need to go, we need to add in other senses as well, right? This thing, to have true intelligence, you should have something that is embodied in the world. So meaning you have a robot that can walk around and also interact with the world. So we're kind of moving the goalposts for what intelligence is, right? But at least at that time, intelligence is something that today you could say we have reached. Another very famous kind of name here is Rosenblatt, who came up with the idea of a perceptron, a way to model a single human or any sort of neuron mathematically. And then he built like a machine with lots of these perceptrons, or not lots, a couple of these perceptrons in it. And he was able to prove that you could give that machine an input of a very low resolution black and white picture, and that it could tell whether a certain object was present in that image, yes or no. And he worked together with the US Navy at the time, and they did a whole conference around it, and they invited journalists. Rosenblatt was a very good salesman, and already at the time he said, well, this is just a start. We're very close now to a machine that will be able to walk and talk and see and even reproduce, right? Of course, that didn't happen, because what followed afterwards is Minsky and his colleagues wrote a paper on the limitations of this perceptron style of model, and this ushered in the first AI winter, or dark age of AI. They basically proved that the way how Rosenblatt and friends were setting up their modeling approaches could basically do no better than linear models in the extreme. And they knew how to make models deeper. So theoretically, they knew a way around this, and they already could prove, okay, if we could hand-tune the parameters of this model, we can kind of show that we can also solve nonlinear problems, but how to train this automatically? They didn't immediately figure this out. And this took some amount of time, and people basically forgot about AI or neural networks and said, well, this is never going to work, until some years later, where Geoffrey Hinton and some other people start talking again about how do you train deeper neural networks with a couple of layers, and they come up with the backpropagation algorithm. And suddenly interest is revived again in artificial neural networks, mainly with this MLP style of architecture. But next problem, we want to make them deeper, we want to make them smarter, we know how to train them, but pity, we do not have the compute power. So again, we get stuck. So again, second AI winter, and the conclusion is, well, this is a nice idea in theory, right? But it doesn't work in practice because computationally it's too heavy. And meanwhile, another person, Vapnik, had come to the US and had basically shown that he had some alternative called the support vector machine that was way more elegant, mathematically speaking, required way less parameters, was easier to train, and could reach better results than the deep learning, or not even deep learning, the neural network architectures at the time were able to do. Second AI winter, people say, oh, well, see, we should become more theoretical in nature. That's what you do as a field. If you notice that you don't have the compute power to train larger things, and you become more theoretical, right? And you follow kind of the SVM-based approach, and it disappeared again. Until 2010, or the 2010-ish, right, where this idea of larger neural networks pops up again, and especially with the arrival of what is now known as AlexNet. We'll take a look at AlexNet. Deep or neural networks enter the stage once again. So this is kind of the overview of that. Now, to give some examples, like in terms of interpretability, this is an article from Byte magazine from '89, where it already shows that people are trying to figure out, we have trained a small neural network architecture with just one hidden layer, only a couple of neurons, and we've utilized that to build like the first crappy version of a self-driving car, right, where it can go left, right, backward, forward, and that's it. But already kind of the question was, okay, now how do we open up this black box and try to make sense of, is this thing looking at edges, or what is this now actually trying to look at? Now, it was only around like 2006 that this became really viable. This is also the reason why people were not using simple artificial neural networks for tabular data, because it just didn't make sense. And there was no way that you could make them really much deeper or larger, because computationally that was not really possible. Until 2006 and following, where Geoffrey Hinton picks up this idea again of deeper networks and starts to think about ways, okay, maybe you cannot train a whole large network in one go, but what if you would start with a smaller version of that network and you keep adding layers on top of that network and kind of trying to train it up sequentially, if you will. Maybe that's something that would allow us to make networks deeper. And other research papers, they began to pick up on this idea. And around the same time, there was a competition that was organized by a research group at Stanford. And the competition was around, or was called the Large Scale Visual Recognition Challenge, and was coupled with the release of a data set of images. And the data set of images was called is still called ImageNet. And the idea was is that the organizers of the competition had collected a couple of million of images, and small images, postage-sized, stamp-sized images, so not large, but color images, and interestingly, categorized into 1,000 categories. So a quite difficult challenge for a computer, especially at the time, to say, okay, I have here a very small picture that I've taken, amongst which of these 1,000 categories does this thing fall into, right? And hence, participants that were trying to play in this competition, that were taking quite traditional computer vision-based approaches, things that you will still find in things like the OpenCV library, like featureization and edge detection and Sobel filtering and stuff like that. They didn't do very well. They were all like hanging around the same error rates, with the top models having an error rate of 25%, which is not that bad, meaning that in 3 out of 4 images, they are able to say the correct category out of these 1,000, right? So that's actually already not bad, but in 1 out of 4, they can't. And if you compare that with how a human does way better on this task. In 2012, Hinton, together with colleagues, amongst with Alex Krzyzewski, enters this competition, and they make a radical choice, and they decide to utilize a neural network architecture to play in the competition. One of the few who would think of doing that, because everybody thought that that was not a viable approach anymore. And it's this that basically unleashed deep learning as we still know it today. It's from this that everything else kind of followed. They had some initial insights that made everything work well together. One insight being, yeah, compute power, we were 2012. If you look at this problem today, we have something like a graphical processing unit in computers nowadays. And people utilize these to play games, mainly. And maybe they utilize this for 3D modeling, or maybe they utilize this for Bitcoin mining, right? So stuff like that, although I'm not sure. In 2012, I guess, maybe on the edge. Not sure when Bitcoin was released, but anyway. But if you look at especially what the things that you need for 3D modeling and operations in 3D, something that games also heavily use, a GPU needs to be very good at executing simple operations on a massively parallel scale. And one of the simple operations that a GPU loves to execute on a massively parallel scale or matrix multiplications, because it needs that for affine transformations, for rotations and translations, and for shader operations that you execute on your pixel space or vertex space, whatever. It loves to do matrix multiplications, and a lot of them at the same time. What do you need to train a neural network? Matrix multiplication. So they said, hey, wait a second, and NVIDIA has just released this library that allows you to define computational statements over a GPU. Why is everybody using a CPU? Let us train this thing on a GPU instead, and let's go much faster that way. there was no TensorFlow, there was no Keras at the time, so they had to come up with their manual implementation, if you will. If you look at what the DeepSeek people are doing nowadays, they also go directly to the CUDA library, and they also bypass these TensorFlow and PyTorch kind of stuff. Just goes to say that there is sometimes merit in coding straight to the metal. That's what these guys did as well. Second, people knew that if you make networks larger or deeper, that the training doesn't go so well, so they came up with two ideas to tackle that. One being dropout, a way to reduce overfitting, and one being ReLU, the Rectified Linear Activation Unit, which is a way to improve the training or the convergence of training of a deeper model. And that's mainly it. The other part is that it's a convolutional neural network, but that was proposed previously by Jan LeCun decades before, so that was not really new. So it's mainly like GPU dropout, ReLU, that did the trick, and they were able to blow the other participants out of the water. In one fell swoop, they cut the error rate in half, whereas the years before, people were hanging around the same error rate. So this has become now known, this network, as AlexNet, and since then, we have seen kind of the emergence of deep learning, not only in the image domain, but then also following that in the textual domain, obviously, and audio and multimodal stuff as well. So from this point, we have seen lots of different architectures. We have seen software support. We have seen new optimizers, new activation functions, new architectures, and so on. So since then, there has been no stop to this whole kind of idea. And what's also been noteworthy is that today, if you look at deep learning as a field, that it's very experimental, very empirical in nature. If you would be someone who likes theorizing and theory building and asking the question, why does this work, rather than what works, you will not always find easy answers if you look around, especially recent papers where today this is the case in language models, where people just stick ideas and try to throw things at the wall and seeing what sticks, right, as the saying goes. So if you look at companies like Anthropic, but also OpenAI, that's basically what they're doing, running lots of experiments, and from time to time someone comes up with a clever little thing like the attention mechanism basically was, because the attention mechanism is basically just taking like a dot product, as we will see. So it's very experimental, very empirical, which for some of us it's fun, right? But you could also say, okay, maybe if you would first take a step back and maybe think a bit more from a higher level, would also from time to time not be a bad idea. But this is how it is. Nowadays, that's what the field looks like. Today, are we close to artificial general intelligence? Maybe. It depends on how you define artificial general intelligence, right? What does it mean to be artificially general intelligent? Typically, people will say, well, it's about generalization, the fact that you can easily adopt new tasks that you didn't see before, that I can buy a robot and have it in my kitchen, and I can basically tell it, look, I know that you never saw white eggs before, but this is the same as a brown egg, so things like that, right? Are we close? Maybe, or maybe we're close enough to fake it, right? Is it necessarily the case that to reach intelligence, it should be exactly the same as how our human brain works? Well, no, not necessarily. We know that these things consume way more power, that they are trained differently, that they do inference differently, but maybe that's not a huge problem. Does that mean that consciousness automatically follows from intelligence or not? Those are all interesting philosophical debates to be had, right? Does it mean that the AI will kill us if it becomes too intelligent? Whatever, who knows? Doom and all of that stuff. What is true is that there is a bit of speculation going on that we are reaching kind of the edge of what is possible with the models that we have today, that we are reaching the extent of the scaling laws, as people like to say, or that we are running out of data. And hence there will be a third AI winter that will arrive. Even although that might be true, the things that we already have reached are already, I would say, valuable enough, and we didn't fully extract all the possible value for or from the current applications yet. So whether it will be like a complete third AI winter, at least from the technological angle, not really necessarily so. Maybe more from a political or cultural angle, that's always to be seen. In terms of software, there's been a whole bunch of libraries that have been proposed over the past years to help you construct deep learning models. And you will notice the reason why this is a bit important to mention is that here you typically move away from your standard Python setup where you install your pandas or your scikit-learn and your NumPy. So typically what you need here is something that kind of looks like NumPy, so that gives you access to linear algebra for higher rank constructs, so for tensors basically. and where these operations that you define on them can be executed not just on CPU, but preferably on GPU. And then the other thing that these libraries typically offer to make them deep learning libraries is a way to do automated differentiation. And we'll see why that's necessary in a couple of slides from now. On top of that, they typically also then add in some pre-built layers that you can utilize, or pre-built types of neurons that you can utilize to construct your networks from. What are the largest one nowadays? I would say PyTorch, which is a follow-up from Torch, a Python version of Torch, which is maintained by Facebook, which is favored by researchers, which has seen a bit slower adoption in industry, because as is always the case in industry, they first start with a particular thing. In this case, that was TensorFlow, and then they find it hard to switch to another thing. But especially if you look at research papers, a lot of them will be utilizing PyTorch to kind of implement their architectures or implement their models. So the other one is TensorFlow, which is kind of a follow-up from Theano, which is maintained by Google, which is also still very popular, has a very strong industry adoption. So that's those, you could say, are the main ones that are being still in use today. There is also Keras, which for the first two versions had the goal of offering like a higher level API on top of an engine like TensorFlow or like something, or like Theano or like CNTK. So what Keras did in the first version is the aim here was basically to say, well, you have these different libraries that people are using, but they tend to be a little bit hard to use. And if you want to convert code that you've written for TensorFlow to something else, that's like some work that you need to do. So we're going to add or put ourselves on top of this. So you only need to write it once. You can write it in a way which is a little bit more convenient. And then you're free to choose which underlying library that you want to utilize to execute it on. Now, issue, Theano went away, CNTK went away, so there was only TensorFlow left. Google said to the creators of Keras, they said, well, you know what? There is still value in what you have done, even although now we are the only engine that you support, because TensorFlow can be a little bit cumbersome, can be a little bit of low level for newcomers to utilize. So we will kind of adopt you as our high level kind of API. If people want to get started with TensorFlow, but they want to do that in a way which is convenient and easy, then they can utilize our kind of Keras way of doing that. This lasted until version 3 of Keras, where they decided, yeah, but wait a second, this is typically Google. Google, in the meantime, had created an alternative library to do deep learning stuff with, which is called JAX. And a lot of industry people are still using TensorFlow. If you look at internally what Google is doing, most of the Googlers have already switched to their JAX thing, which is not bad either. Meanwhile, we have had PyTorch as well. So the Keras developers were going, yeah, but wait a second, now we have these multiple engines again. Isn't there again kind of a reason for us to now become a multi-backend? And so that's what they did in Keras 3. They're now supporting these 3 backends. So again, they're not closely linked to just TensorFlow anymore. They still aim to provide an easy way to get started with deep learning and then choose your backend yourself. Why am I emphasizing this is because for assignment number 2, you're free to choose what you want to utilize. I would heavily recommend you to utilize Keras. You will find the most tutorials there as well to help you out. If you really want to go straight to PyTorch or straight to TensorFlow, be my guest. You can do that as well. But typically, Keras is the easiest library to get started with. There are others as well. If you really like Julia, there are things like Flux, for instance, but these are lesser well-known, lesser well-used, utilized, so a bit less important to discuss. Okay. With this being said, what it's now about in terms of foundations. I've already mentioned we're trying to kind of model a mathematical version of a neuron. So we're going to introduce neurons. What makes a neuron in our world? Well, there are a couple of things that we need. So what can neurons do? First of all, they can take in inputs, which are, you could call these values coming from other neurons or signals, right? They don't have to, but they can take in inputs from other neurons. Secondly, they can define or they will execute some sort of operation which needs learnable parameters or weights, right? Which are the things that we will learn during training or estimate, if you will, during training. But they don't have to. Also, this is optional. Not every neuron comes with its own weights, as we will see. At the very least, what you will see that a neuron will always do is it will be able to generate some sort of output. It will be able to provide some sort of activation, some output signal that it produces. Depending on the source that you look at, some people will say, well, that activation needs to be a single number, right, which is not necessarily the case, right? As we will see later, sometimes it's also a matrix of numbers. It needs to be -1 or 1, which is also not the case, right? So let's just first take it very abstract and say, well, a single neuron can produce an activation, can produce an output. Okay, let's try to make that a little bit more concrete. Here we already have one type of neuron that is being listed, and these are input neurons. And as you can see, we have 3 of them plotted here. And so these only serve to act as kind of entry points to feed in an instance that we have, right? Think about a row in a data set, or think about a single image, right? Something like that, and feed that into the rest of our network to do something with that instance, right? And typically the do something with will be is we will want to make some sort of prediction from that instance, right? So here, if we have one person with an age of 30 years old and an income of 1,000 euro and a gender of female, let's say, well, these neurons are just there to represent that instance and to feed that into the rest of the network, right? What can we learn from that? Well, these input neurons, obviously, they do not have inputs of their own, right, because that's where we start from. They also don't have their own weights, right, because they don't need to learn anything. They are just there to feed in an instance to the rest of the network, right? And this also tells us that the activation that we see here from these neurons, but also from the other neurons that we have in our network, that the activation will obviously depend on the particular input that we've given this network, right? Because already for this case, if I would give a separate instance or a different instance or observation, of course, these 3 values that they spit out, that they activate, are going to change. Now, with this, you can't calculate anything. So what's the actual perceptron unit? Well, that's the triangle that you see there. And here we say, well, this single perceptron unit is connected to all the input neurons, as you can see. So all the activation values that they output are being sent to this perceptron, and this thing is going to perform also an operation to provide its output or its activation. What's the operation that a perceptron unit performs? Very simply, you take a sum of products. You sum every input that you receive, meaning the output, in this case, from one of these input neurons, and you multiply that with a W. And what's a W? Those are these learnable weights. Those are these learnable parameters that this perceptron unit defines. So here, the number of weights that this perceptron needs is not even something that we can pick. The number of weights is equal to the number of connections that it receives, right? Simply because it's connected to every input neuron. That's all. Now, that's not very special. So typically, the way how a perceptron produces its output also involves a secondary step. And that secondary step is we're going to take this sum of products here, and we're also going to squeeze this through what you can call like a squeezing function or an activation function. And this is something that the user or the architect of this network can choose, what that function should be. Now, what these weights will be, well, probably we're going to tune them in some way, right? We can start with a bunch of random weights for this W1, W2, W3, but you can kind of, or hopefully you already start to notice here that the whole process of training is exactly to modify these weights to make them better and better for some task, right? Meaning that once we are finished with training, that these weights will remain fixed, they won't change anymore, right? But the outputs that this perceptron can give can still change because that depends, of course, on the activation that these units are sending. So it depends on the instance that I'm looking at, right? So activations are instance dependent, weights or not. Typically, what else do? We add in a bias weight, right? So we just say this is kind of comparable to an intercept in a regression model where the input or the activation from this unit is always 1. So we just end up multiplying 1 with this learnable parameter and we stick that in as well. You can split up this kind of operation and this operation. If you want to, you could call this 2 separate neurons already in your network because one is basically making a sum of products and the other one is squeezing that through an activation function. Very often they are just defined as being the same unit or in the same goal. Now, if we then say, wait a second, if as this F over here, if I make that a sigmoid, then we end up with something that is very recognizable, right? Because then you get as an output here something which is between 0 and 1, right? What is this? This is logistic regression, basically. And if I then ask the question, okay, how do we determine the weights, or how do we estimate the weights? We saw previously that probably there exists some, or hopefully some closed form analytical formula that helps you to do so, given that your input set is full rank, or that you don't have these collinearities going on, and given that you use a nice loss function, such as the squared error, because that's differentiable, and from there you can then derive your closed form analytical solution. Now, that's not going to fly anymore here, because we're going to deviate from this simple architecture in a second. We're going to add more layers, and we're going to maybe use different activation functions, and maybe we don't want to utilize the squared error as our loss function, but we want to utilize something else. So yeah, good luck finding like a closed form derived analytical solution. So we need another procedure that can help us to, for any sort of network that we will define, for any sort of loss function that we will utilize, to estimate, or to iteratively, in this case, find good values for these weights. And that procedure is called gradient descent. That's the optimization technique that we end up utilizing for taking a function that we want to minimize, namely the loss that we have, given some learnable parameters. Is this the only optimization technique that you could utilize to do this sort of stuff? Well, no, XGBoost is also using the second partial derivative rather than only the first partial derivative. There are things like genetic algorithms that you could utilize, or particle swarm optimization that you could utilize, right? Why don't we use the second partial derivative here? Why only the first one? The second one would be better because that's slow and annoying to implement on a GPU, right? So this turns out to be something that works well for a whole bunch of loss functions, for deeper networks. This is easy to implement on a GPU. Doesn't mean that these other optimization techniques have not been tried out from it, but this is the main one that we utilize. Sometimes you will, or this is an excerpt that I took from a tutorial where it says, well, this is the formula of gradient descent. Basically what this says, if you would like to know what the next value for a particular weight should be, so maybe let's say this one, W1, right? So you start from a certain starting value, right? Let's say 0 for all of the weights. Take the previous value minus some lambda times the partial derivative of the loss function with respect to that weight. Okay, yeah, why does that work? What does this mean? And it will also say that for a simple perceptron that we had so far with the sigmoid, we can basically utilize this formula, and this is something that you can then straight implement in Python, right? The learning rate here is this lambda parameter, and this is basically a user-tunable hyperparameter. Okay, why does this work? Well, let's say that you use squared errors as your loss function, and you have 2 weights and a bias weight. So you only have 2 input features to make life easy. Well, basically, it's just working your way through the gradient descent formula as it's listed here, right? So we can do so. And we can say, okay, what I need here to make this work is lambda I can set. The previous value of my weight I know. So the only thing that I really need to work out is this partial derivative over there. Okay, partial derivative of the loss function with respect to a certain weight I that I have. This is my loss function that I've chosen, right? The predicted y, subtracted from the true y. I square this with respect to this weight. Then you can apply like this little chain rule trick where you decompose that, because these 2 cancel out anyway, right? But they can bring the 2 in the front of here, right? Because this does not include this wi. So this is just easy to figure out. There is still this thing left that you need to go through. But you have this minus here of this estimated value. This is just a scalar, right? So you can also bring the minus in front. So now there is only this thing to work out there. And then you can say, well, we utilize, we know what the predicted y is. That's basically the sigmoid function of w1 times x1 plus w2 times x2 plus this bias, right? Let's call that O. So it's basically the sigmoid of O, right, over O. And then we use that chain rule again. And then this thing, to figure out this, you can look up the first derivative of the sigmoid function on Wikipedia, which is this, right? So you just copy-paste that in, and then there is only just this O with respect to the weight that you need to figure out. And that's easy because that you can just take directly from this formula. That's either, if you're looking at W1, that is X1. If you're looking at W2, that is x2, right? If you're looking at the bias weight, it's a little bit special because then it's just 1, right? But basically, if you're just looking at W1 or W2, it's xi that you can stick in there. And then you reorder this a little bit, this whole mess that you have derived, and you come to something like this, and you have your solution for the first partial derivative of the loss function with respect to a given weight. And then if you plug this in into this formula, right, minus minus becomes plus. You do need the expected minus the predicted value, so that's what stays here as well. You do need xi, right, as well. The only thing that kind of remains, this 2 over here and this sigmoid of O and 1 minus the sigmoid of O. Well, the sigmoid of something, we always know that that's, or we know that that's a value between 0 and 1. And 1 minus the sigmoid value of O, well, likewise. So basically, the first partial derivative of the sigmoid function, which is the thing that we wrote down there, is basically just a small value between 0 and 0.25-ish, right? Whatever we put in. So to make life easy, we could just say, well, take this 2, take this thing, and you already have this learning rate that you can tune anyway. So just drop this and just let the user specify this through the learning rate to simplify the formula a little bit. And that's how you come to this kind of simplified formula, but given that you use squared errors as your loss function. So then what is this learning rate? What does this boil down to? Well, what we are basically trying to figure out, if you try to think of it a little bit more in visual terms, is I'm trying to figure out by taking, so in the example I had 2 weights, W1 and W2, and I know that I start with a particular starting configuration for W1 and W2, and I can calculate my loss at that point, right? Because I can just take, well, how would I calculate my loss? I have this network. I can take all of my data instances that I have. I can run them from left through right through my network to get predicted values. Then I can calculate the difference with the true value squared for all of them, right, and average all of them by the number of instances that I have, and that's my loss, basically. So I can calculate some value of loss at this position for my 2 weights. What does the first partial derivative tell me, right? Well, from that I can learn basically the gradient of this loss landscape. I can't see the full landscape, right? But I can at least feel what the gradient is in this position, meaning what's the direction of steepest descent. That's basically what the gradient tells me. Like, it gives me the slope, as you have here in the single univariate thing. If you take the first derivative, people have told you, well, that's the slope. If you're like in a multi-dimensional kind of thing, you don't just have the slope, but you also have the direction that you go the steepest in, right? If you know the direction, well, this gives you an idea of, well, in which direction should I step to make my loss function go down, right? Because I'm standing here currently, and I know that I'm going the steepest in this direction, so I will know that I will have to take a step forward in this direction to make my loss lower, meaning that I do know my weights. Do I need to go that way or that way? Do I need to go this way or that way, right? What I don't know, and similarly with this example, is if you have the first derivative, you know the direction, and you know the slope in which you need to go lower, right? In the case of here, you can only go to the left or to the right because you only have a single weight, so that's easy to see. But you do not know the size of the step that you should take, right? That's only something that the second partial derivative can tell you. So that's why we need the learning rate. And the learning rate tells us, well, based on, of course, the size of the step that you take can be dependent on the steepness of the slope, right? You can kind of feel that if you're looking way downwards, that maybe you can take a larger step, right? Then when you're already kind of in some kind of plateau. But you do need to take like a size of your step dependent on the slope that you currently are feeling. So likewise with the gradient here, you might know that you're going very steep with W1 in this direction, and not so steep in W2 in this direction, right? But you still need to take a step in this direction and in that direction. But do you take that halfway here or times 2 for both of these cases? That's something that you don't know. And that's something that this lambda value or the learning rate determines. It's a crucial hyperparameter. It's the key hyperparameter of how gradient descent works. And what's kind of the, yeah, question? Yeah. Yes. Yes. Or yeah, an adaptive kind of, yeah. So we will see two examples of this in a second. But in the basic case, none of that. So same multiplication for each weight and always the same multiplication. So it's fixed as well. Yeah. So that's a crucial thing to configure because, and that's indeed you can already feel maybe not ideal because if you take your learning rate or your step size too high, in the beginning you will converge rapidly, but then you will kind of bounce back and forth once you are reaching like your minimum. If you set it very low, well, then you risk getting trapped in one of these local minima, right? But also you will need a lot of iterations before you end up in this minimum as well. So it's typically kind of, yeah, a bit of tuning that you will have to perform to find the best value for this learning rate. So the error or your loss is a function of the weights given a piece of training data. Our goal is to minimize the error using the gradient of that loss function, and gradient descent is then just a process of following this, and ultimately you will end up in a good position, but the learning rate will determine your size of your steps. What do we mean by an iteration here? So like one arrow, what is then one iteration? Well, in you have different versions of this, right? So typically, what deep learners will utilize is every time you have utilized all of the training data that you have available, that's called one epoch of training, right? One round of training. Typically, you do not figure out your best positions for your weights after only one epoch of training, and you will need to do a couple of passes over your training data. Typically, you also shuffle your instances before every epoch, right? Otherwise, otherwise there can be a little bit of noise going on or entering based on how you ordered your instances. So typically, you shuffle them as well. What we can then do is differentiate between at which point do we update our weights. The example that I showed here is I said, okay, we have a particular configuration for our weights. We pass all of our instances through the network. We calculate all of their outputs. Based on that, we calculate all of the losses and we average them. So this means that to perform one weight update, we need all of our training data. We basically need to perform a full epoch. You could say, well, that takes time, right? It's a bit of a waste that you're using your million instances to only move a little bit in your weights. Another form could be, well, do it after every instance, right? Use your first instance, calculate the output of your network, compare that with the expected output, calculate the loss, and based on that loss value that you see, move already a bit your weights. And then use the second instance and the third instance. So then you do as many updates as you have instances in your data set. And still you can then do multiple epochs of that. That's typically called stochastic gradient descent. So the difference being, do you perform a weight update after having given it a full data set or instance after instance? Now, what's the problem with this whole sigmoid idea is that, yes, you can train your weights like this, but you still just have logistic regression at the end of the day, right? So if you give it a data set like this, which is the famous XOR problem, no matter how you try to cut a line through this thing, you will never have a perfect prediction score. You will never bring your training loss down to 0 by doing this. You will always mispredict one instance. And probably your weight values will end up in a situation where maybe 2 out of them are correct, or 1 out of them, well, here 1 out of them is correct and 3 others are not. So this will never converge to a good loss value. So our network here would then simply not be capable to learn this. Okay, no problem, because we know how a single perceptron works. Let's just connect them like in a human brain. And then you come to your first true deeper architecture, which is a multi-layer perceptron network. And a multi-layer perceptron network at the very limit says, okay, your input layer, you don't have a lot of choice there because you need as many units as you have features, right? That's kind of, you're stuck. Your output layer, you don't really have a lot of choice there either because this will probably depend on the task that you want to do. If you want to do binary classification, very likely your unit in here is going to be something that uses a sigmoid activation and is only going to be a single unit, right? If you want to do multi-label classification and you have 3 labels, well, then you probably have 3 perceptrons in this output layer, all of them with a sigmoid activation unit. If you want to do something like multi-class, then you probably have as many units in this output layer as you have classes, but then with the difference that not every output needs to be between 0 and 1, but the outputs altogether of all the units in this output layer need to sum to 1. Right? And none of them can be higher than 1 or lower than 0. That's then called a softmax activation that you apply on multiple units as a whole. So the only thing where you can really change up your architecture and play around with it is in this intermediate hidden layer that you add. And there you can pick how many units, perceptrons, do you want. And you can also choose which activation function that you want to give them, right? So we can play with how many units per layer, which activation function. We could even add in multiple of these hidden layers as well and stack them on top of each other. And that's basically what makes our network deeper. Only issue is that even with this thing, how do we train this? Because now, every arrow that you see here is associated with a weight that needs to be learned, right? And we're not even plotting the bias weights here, but those are in there as well, right? So I already have way more weights than I had previously. How do I train them? What I can still do is I can feed forward something left to right and go through all the calculations, and I can get my final output on the right-hand side and compare this with my true output. I still have that. I can calculate my loss here, but to know how I should update these 2 weights, I kind of need to have some estimate of, I know what the output here is. I can also calculate that left to right. I know that. But I really can't compare the output that I get here with, yeah, but what is the desired output there? I don't know, right? I only know the true output at the very end, but the true outputs for these, I don't have a concept of their perfect output, and there might be multiple good conditions that exist for their output values, right? Because in the end, they're recombined by this guy as well. So I don't know that. So this is the thing that took some time to resolve. And eventually, the people came up with a quite simple solution where they said, well, what we can then at least do is we will simply work our way through it by applying the chain rule of first partial derivatives in a stepwise manner. And we start from the right-hand side, and we kind of propagate the error that we see, right? That's why it's called backpropagation, from right to left to kind of get some estimate of what should your desired output here have been. And we kind of work our way from right to left that way. The issue being that, let alone that you try to work this out manually, even for a simple network like the one that you see here with 2 hidden layers, this already becomes quite complex. But the idea in itself is actually quite simple. Feed forward is simple. You know what the output is in the final layer. You can compare that with the expected output, so you can get some loss value from there as well. From that loss value, you can basically work out how you should update this weight and this weight as well. And then from there, it's basically applying the chain rule of partial derivatives to kind of work out how you should update the weights before that. But you do that in kind of a stepwise manner where you first update these 2 weights, and then you use their values to work out what the updates in the previous layers should be. You don't need to know, or I will never ask you to kind of write this down manually, because no one does, right? This is crazy to do. Imagine that you have a network with 80 million neurons. You're not going to use this, right? This is exactly what software libraries brought to the table, is that they allow you to specify what your computational graph should look like going left to right. And hence why libraries like PyTorch, they call that their forward pass or their forward function. That's the thing you need to define. And they're smart enough to figure out that if you stick to their defined linear algebraic operations, to know this is the computational graph that you have defined. You have specified how to do it left to right. I can figure out how to differentiate these weights in a backpropagation path from right to left for you, right? So then you're kind of released from that effort to do that manually. You can check these YouTube series of 3 blue, 1 brown. If you like to look at animations, very beautiful ones, if you like to get like a refresher of the things that we have just discussed. Now, in any case, on the question of how big do we now need to make this network, how many layers do you need? there is at least a theorem that makes life easy for us. At least, well, that's why it's a theorem. In theory, it makes it easy, but in practice, it does not. And it was quickly proven that if you only have a single hidden layer, so you basically have this thing, and you add in enough neurons in that hidden layer, and you have enough data, enough training data, and you have enough time, that basically with this architecture, you can fit any sort of data set perfectly. You can get a perfect training loss. Right? So basically what this says is that this thing can fit everything as long as you use enough neurons, as long as you give them probably non-linear activation functions, right? And you train them for long enough. So why do we need deep learning then? Well, of course, because this is a theoretical construct, because you can feel that the number of units that you need in this single hidden layer as your data becomes more complex goes up like this. Whereas the number of units that you need if you spread them over multiple layers probably goes up like this. The data that you need, same thing. The time of training, same thing. So yeah, you could just do it with one layer, but at some point it's not going to be economically viable anymore to do that, right? But theoretically, they can. This is the discussion on automatic differentiation, right? So what you could do if you specify your forward operation, so you have some function, some neuron that does something, right? And you can write it down like this, and you say, okay, the output of my neuron, right, is defined as this and this and this and this, right? Why does this specific thing, whatever, right? Doesn't matter, but this is how I specify my forward operation. Now I want to train this thing, right? I have some parameters that I'm free to change. So to do that, I need, and I'm using gradient descent, I need to figure out the first partial derivative. Yeah, we could try to work that out manually. Like you saw in high school with all the tricks of differentiation that you can apply, right? Some mathematicians find that this is a very pleasing sport to execute, right? Or brain teaser. Most people do not, and especially not once you come to the point where you have 80 million parameters to work your way through, right? So what you could then do is some sort of symbolic operations. This is kind of the Wolfram Alpha style, where you try to define symbolic operations that you can define, and then you let the computer work their way through them to do that instead. What you could also do is like, this is the Excel style of approach, where you say, well, I don't want to work my way through the algebra, but I could basically test it, right? I have the forward operation of my network, so let me try moving W1 with a teeny tiny step up and looking at how the loss function changes, and a teeny tiny step down and looking how the loss function changes, and that's probably going to be like some approximation locally of what my actual steepness would look like, which, to be honest, in a lot of cases doesn't even work that badly as long as your network does not explode. Automatic differentiation says, well, no, we keep track of your full computational graph, and from there we derive the backwards looking graph. And the nice thing there, or with this approach, is that you can even then in your forward operation have the liberty of programming in with constructs such as for loops, with control flow constructs, and that also in the backward pass, basically this gets executed in the correct way as well. So this is a large benefit that these libraries bring to the table and basically prevents us from having to implement that manually. So basically every package like TensorFlow and so on implement or utilize automatic differentiation based on the inspection of computational graphs, which links your operations over higher rank matrices together. And how it turns out, a decent autograd tensor library is 90% of what you need for neural networks. Then you have an optimizer like SGD, as we have just seen, stochastic gradient descent, or one of the others, and some boilerplate code for your training loop, and then you have all you need. So that's basically what most libraries add in. Okay, we will go for a little break. Before we do that, last demo before the break to kind of show what we have just seen off. So this is basically the architecture as we have just seen it. Two input features, X1 and X2. And the data set that I want to learn is this thing, right? So I have one perceptron. I have the two weights that I can visualize here. I have an activation function that I can pick, which is probably, let's say, sigmoid, but of course 10H would also work, right, to split these two classes up. And here we have the learning rate. Here you see the number of epochs that I've been going through my data set of training. I can keep track of both my test loss and my training loss, and they both go to 0. This thing fits perfectly, right? That's the idea. Uh-oh, problem. We have now a data set that looks like this. I train again. My test loss stays at 50%. My training loss stays at 50%. This thing can't fit this XOR problem anymore, right? What would we have done in the past? We would have said, well, maybe we add in an interaction term, or we do some feature engineering, and then with a simple linear model, look, you can perfectly fit this data set as well, right? It's kind of the manual feature engineering as you would have done previously. Yeah, the interaction term is enough, and you also see that based on the weight value, that's what my model ends up utilizing. In neural networks, we don't want to do manual feature engineering. We say, well, screw all of that. We just want to start with the raw features that we have. Instead, what we do is we add a hidden layer, right, in between. How many neurons is enough? Is 1 neuron enough? Well, I don't know. Let's try. It does a little bit better, right? It's at least starting to fit something, but it's certainly not perfect yet. So maybe I need 2 units to fit this perfectly. And the universal approximation theorem tells me that I can just continue to add in stuff here until it starts working, right? So I try with 4 units, and now you see, well, the fit is getting better and better around this data set. Let's do even more. Right, until, now my test loss and my training loss, they're really going to 0. I'm perfectly fitting this data set over here, right? What else did we see? Learning rate, crucial hyperparameter. I know that if I set this higher, probably the speed of convergence will be better, but at some point, this converges indeed much better. I didn't have to wait for so many epochs. But at some point, if I set the learning rate too high, right, this thing is going to start doing crazy things, right? You see here that I get spikes in my train loss and in my test loss because it's kind of going into numerical instabilities, or it's like overshooting also these local minima, so it's not doing well anymore. If I set my learning rate too small of a value, it's going to converge, but you can see like these loss functions, we're going to get there very slowly, right? And maybe I will end up in some local minima, so there is not a lot of activity that's happening here as well. So that's basically the idea. If you then look at the other things that are being shown here, what's regularization? You can probably guess, right? We have seen it from previously, is that we add in the values of all the weights that we have here into the loss function, either lasso or ridge. Well, let's regularize a little bit. Maybe then I can use a higher learning rate as well, right? And this would still work. Well, maybe I'm regularizing too much, right? So then you can start playing with this and seeing what this does. So those are the hyperparameters as we have seen them currently for the standard setup. You could also say, well, why use just 1 hidden layer? Why not use like 3 hidden layers with 2 units each? Would that also work? You can play around with that. Oh yeah, indeed, this also works, and the loss looks quite differently and so on, right? So if you know this, you basically know 90% of what there is to know about deep learning already. The only things that we will start, or that we'll play with a little bit still, is, okay, then which loss functions can we utilize? What's the actual architecture? Maybe you have styles of units that output or perform another operation than the sum of products plus an activation function that we have just seen for the case of a perceptron, right? And so those are basically still things that remain to be seen. But basically, this is how deep learning works, right? So don't think that deep learning means that this network is kind of getting some deeper understanding by any means, right? It's just meaning that we have more layers, making it deeper. A better name would have been layered representational learning or differential functional learning, because that's basically what we're doing, right? Today, if you look at neural network architecture, so it's a little bit magic here, is that many of them will contain hundreds of layers after one another. And that it's kind of weird that even with 80 million parameters, that this idea of gradient descent works in exactly the same way and can still work, but that is exactly what's happening here. Okay, next step is looking at a couple of examples, and I'm moving to our CNN, but first we will go for a, let's say, 15-minute break. All right. So based on the MLP, what you have just seen is, if you look at the image domain, at least this allows us to come up with something that's already a bit more intricate, or would work for images as well. Probably you will need more layers than just a single hidden layer, but you can make certainly something like this work, especially in the case when you work with tiny images. So let's say our goal is that we have images like these, 28 by 28 pixels, grayscale images, right? And we would like to recognize the digit that's been written in the image, something from 0 up until 9. So what can we do, or how do we set it up? For input layer, it makes sense that we have an input neuron per pixel in our image. So we have 28 by 28 input units, right? And they will, let's say, output a value of 0 for a black pixel or 1 for a white pixel, and then everything in between is some sort of grayscale value. Then to basically to be able to define our operations in the following layers a bit more concretely, or a bit more correctly, we're going to add in perceptron layers. So we first will convert this 28 by 28 grid or matrix of units, if you will, to just something that looks like a flat vector. That is just an operation to kind of reshape or tensor a little bit. So this flatten operation learns nothing. It doesn't need to learn anything. It's just kind of a reshape that we perform there to go from a matrix to a vector. And then we can add in an MLP layer. So typically that's called a dense layer. Dense here meaning that for each of the neurons in the next layer, so for each of these 8 perceptrons, they are fully connected with all of the 784 units that come before, right? Meaning that for each of these 8 units, we will have to learn 784 weights, right? Maybe even 785 if they include a bias weight as well. Same for these guys, same for these guys. Activation functions, here we will use a ReLU. You could use a hyperbolic tangent or a sigmoid there as well. We'll see in a second why we use ReLU, or what it means to utilize a ReLU. For the last layer, we don't really have a choice, both in terms of how many units we utilize and the activation function that we utilize. We're working in a multi-class setup. We have 10 possible classes, so we have 10 units here, and we use the softmax activation function. Softmax makes sure that the outputs of all of these units are between 0 and 1, and that they are summed to be exactly equal to 1. And then what we will compare this output to? Well, basically to something that looks one-hot encoded like this, and on the basis of which we're again going to calculate some sort of loss value as well to kind of, and to then train all of the weights of our network. And if you train this, and you have enough images, even with this whole bunch of weights that we have here, this trains rapidly and fast, right? And you would even see that the accuracy that you get on this data set with an MLP architecture like this is not even all that bad. You will get like, you can get above 90% accuracy with this style of architecture. Now, what else can we observe? First of all, you would kind of hope, okay, if I would now inspect what this network has learned, how would I do so? Maybe something that you could wish for, at least, is I can take a look at this layer of 8 units that I have, my very first layer that's kind of doing an operation. And if I look at the weight matrix that is learned for this layer as a whole, right? Well, if I'm learning a vector of 784 weights per unit, then I can describe all the weights for this layer as a matrix of weights, or every column describes the weights for one of these 8 units that I have. I could then say, okay, given that I take these 784 weights for one of these units, and I'm ignoring the bias weights here to make the visualization a bit easier, and I would reshape those 784 again to 28 by 28, what I then get is, because these weights then basically represent, well, by how much are they multiplying each of the pixels that they see in this image. And what I would hope to see is that if the weight values are close to 1, that possibly or maybe represents them an area in the image that this network gets excited by or likes to look at, you could say. And maybe you would hope that there is one unit in there that gets excited by horizontal lines being present in the image. And maybe there is another one that gets excited by vertical lines in the image. And so at the very least, you might hope for some kind of insights like these. What do you get if you visualize the 8 weights that these guys have learned like this? Basically something that looks like a complete random mess, right? Not that it doesn't work. This is trained, right? So these are the trained weights. The accuracy is good. But in terms of interpretability, yeah, you can see that there are like zones where indeed the weight values are higher, right, than others. But it's a little bit hard to kind of make sense of. So yeah, in terms of interpretability, we have definitely lost something here. Something else that's important to keep in mind is the question, what if you now try to take this trained network and you let it predict on this image, basically just random noise. You will get back an output vector like this, where it's like heavily convinced with 98% accuracy that this is the number 3, right? Again, this is weird, but also not so surprising. We know, of course, from other models that we should not extrapolate between the boundaries of our training data. It's kind of the same thing going on here as well. If you do expect that users are going to give it noisy images, well, then maybe you should also have incorporated them in your training data to begin with at the outset, right? So don't expect that they will kind of magically distribute 1/10 probability over these different outcomes either, which is mainly the result of that softmax operation. But things like these can still happen also with neural networks. Okay, that's the basic MLP architecture. What else is there to say about them? A couple of things. Activation functions, we have just seen that for the output layer there, the choice of activation function is basically related to the task that you want to do, right? If you're doing binary classification, then the activation function in your last unit in that output layer is probably either going to be the sigmoid or is going to be the hyperbolic tangent. If you want to do linear regression, then the activation function is probably just going to be something that looks linear. If you want to do a linear regression, but you only expect positive values, right, then you can use the ReLU activation and things like that. So there you're typically, or you are bounded by the task that you want to do. Now, that's not the case for the activation functions that we have stuck into these hidden layers, for these intermediate neurons. There we basically are free to kind of be more flexible with the activation function that we utilize. And at the very beginning of artificial neural networks, people were convinced or thought that it is also there good practice to use activation functions that are symmetric, negative domain and positive domain, and had asymptomatic ranges. Again, like something like a sigmoid or a hyperbolic tangent for the intermediate units as well. Nowadays, we have found that these activation functions actually limit training for deeper neural networks that have more layers. And the reason why this happens is due to an issue that is called vanishing gradients. And it took like a surprisingly long amount of time to figure that out, but that's one of the things that the AlexNet paper basically was capable to figure out, and hence why they introduced the ReLU activation function to begin with. The problem is that if you look at how stochastic gradient descent works, or gradient descent with that idea of backpropagation, is that at each layer, we're going to multiply values with the derivative that we get out of the activation function utilized for a particular neuron. If you look at the derivative of a sigmoid function for intermediate layers, and you're working your way from right to left, and you're like, you have just done the weight updates for your output unit, and now you're kind of figuring out how you should update the weights for this unit, and this unit would be using a sigmoid, right? So something like this. And you're over your activation, the sum of products that you get in, of all the weights times the activations, they put you somewhere into this zone, right, into this area. And you then take the derivative of that activation function. What's that derivative going to look like? Very close to 0, right? So the updates that you will perform on your weights, no matter what the output here, or the sum of products was, the updates that you will perform will end up being very small anyway, because you multiply with something that's close to 0, right? So the weight updates that you do on here and here and here and here are going to be very small. Okay, what happens if you cascade that further in your network going to the left? Well, it's only going to get less and less and less and less, right? So the updates that you do to your weights over here might still be reasonable. By the time you have propagated those changes all the way back to the beginning of your network, in those very first layers, you're going to see that the weights change very slowly, right? In tiny increments. And this is what can cause that these networks take such a long time to train if you make them deeper. So that's the issue of vanishing gradients, and that's exactly here. This is shown with a network of 5 layers, right? And it's not so easy to kind of inspect that manually with a toy example. It's hence weird that this took some time to be found. If you look at the layers, so layer 1 is the left one, going to layer 5, you see that their activation values tend to become smaller and smaller, right? So the activation values themselves get closer and closer to 0. what happens to the gradients that we backpropagate in the first, or in the last layer, I should say, right? Because we backpropagate from right to left, so the turquoise one, layer 5, there we see that the changes that we make are still widespread out. We are still making like heavy changes. By the time we have arrived to the first layer, we're barely changing anything as well because our gradients have become so small, right? It's like we have lost all of that steepness in our gradients, so we are not performing a lot of weight updates anymore. Now, the key thing is that the things that we learn in those very first layers also typically tend to be the most important things as well, because it's those outputs which will end up driving all of the layers afterwards. So why it can be difficult to train networks if you use sigmoid or hyperbolic tangent activation functions for the intermediate layers. People came up with two key strategies to solve this, and one strategy that AlexNet adopted was to use a better activation function, and the idea is very simple. Another strategy is to utilize better initialization. What is the approach that they took, or what that was utilized first then? Well, what you do want is you would like to avoid, like is the case with the sigmoid, that you can end up in a zone where your partial derivative gets very close to 0. But secondly, you do want something which is nonlinear. Said the AlexNet, what we will then utilize is just take the maximum between 0 and the sum of products that you take in. So that's an activation function that looks like this. If you have something higher than 0, you just follow along. Right, so then it's and if you have something lower than 0, you just cut it to 0. That's nonlinear, right? And this allows you to make nonlinear operations if you stack layers of this activation function on top of each other. The nice property is that as long as you keep it positive, you have a constant gradient, right? Is this perfect? No. If you would think a little bit about this and you would like make comments about this, you would say, yeah, but then what happens if for some reason you would end up in a regime where you're like spitting out sum of products over here, then your gradient is going to be 0, right? And it's going to be exactly 0. It's probably going to be hard to escape from here once you end up in here, right? And indeed, that's true. So if you utilize ReLU, you can end up with what's being described as dead units that are not being updated anymore because their gradient has become effectively 0. The second problem that you might notice is that this activation function is not perfectly differentiable. There is this spot over here where we can't take the first partial derivative. But that's fine. Automatic differentiation does not care that much about it. If you use a loss function that uses an absolute value, or you use lasso regularization, which also uses an absolute value, you also have something that's not perfectly differentiable everywhere. So that's maybe a bit less of an issue. Later on, people came up with adaptations of this ReLU activation function where they said, well, it's maybe not a good idea to make this completely flat. Probably we should also have a bit of a slope in here, but then a bit tinier than the slope on the right-hand side is. And maybe the slope of this thing is something that could be learnable by the unit itself. So that could be just another weight. Another idea is you could come up with something that looks like more something smooth like this, right? So those are things like the SELU and the GALU. So there have been a couple of different adaptations that have been proposed, but these all try to do away with the underlying issue of vanishing gradients if you utilize something like a sigmoid. Those are the examples that you see here. So it says like the learnable or the parametric rectified linear unit, the exponential linear unit, the scaled exponential linear unit. The GALU is not GELU, is not mentioned there, but this is the one that most transformer networks nowadays utilize actually. So this has become like the, it says it here, like replacing ReLU with GALU. So usage of this activation function was actually a quite important step. If you look at models that use that are built for vision modeling, so convolutional neural network inspired, a very good paper to read through is from 2022, a Confident for the 2020s, which kind of takes a look at what are now all the things that we have found work well in the domain of computer vision if you utilize a convolutional neural network. And one of the things they say is, well, the GALU is a smoother variant of ReLU. It is utilized in most of the transformers. And we find that indeed we can substitute it for a Confident as well, although that the accuracy does not change that much. But okay, it wouldn't hurt probably to substitute a ReLU for a GALU. And the problem of the dead units is the thing that's described here on the slide, on the left-hand slide. That's one issue, how we can solve the problem of vanishing gradients. Another issue is that of initialization. And initialization here refers to, you do need to start from some initial starting value of your weights. And we have said before, well, you can put them all to 0, or maybe you could think about, we just pick some randomly sampled value for all of them, something between -1 and 1, right? So we should think a little bit of, well, how important is it to do that initialization in different ways? And indeed, it turns out to be very important. And the way how people found that out is by something that was described as the lottery ticket hypothesis. And it says, okay, let's say you start with, to describe the idea, let's start that we utilize this network to identify those images with, as we just saw it, which already has a whole bunch of weights in there. And we initialize those weights randomly between -1 and 1. And we then train the network for a couple of epochs. And we keep track of the loss on a train set that we have, right? And on the validation set that we have. Maybe on our validation set, we see kind of behavior like this. It's going down, but it's not going rapidly down. And then we redo that from scratch. We re-initialize our network. So we start with random weights again. And we again train for 10 epochs. Will you get the exact same curve? Well, turns out no, right? For some starting positions, you will see this. For some starting positions, you will get lucky, right? And that's called the lottery ticket hypothesis, that apparently there are like better starting positions than others, right? Which is an annoying problem. It also exists in optimization as a whole, but whatever. So that means that perhaps having a smart idea to initialize might be important. Now, this approach, in older days, what people then did is something called preliminary training, where indeed you just restart a couple of times, right? And you train for a couple of epochs. And then you continue training with the version of the network that did the best so far after a couple of epochs, that had the best lottery ticket. That's the one that you continue training further. But yeah, it's a bit annoying that you need to do like 10 restarts and train it for a couple of epochs, and especially for deeper networks, that takes time, right? So couldn't we just try to be a bit smarter in the initial weights that we put there, instead of just like trying 10 times and seeing which one works best? And so the reason is that what happens, if you think about how you can set up the most simple version of like an extreme deep neural network, is again, it's due to these activation outputs that either explode or vanish away. Either the loss gradients will become too small to have an effect, just as what we saw with that sigmoid activation just now. And if our activations would blow up, yeah, then also the gradients might be blowing up, but we will get into numerical instabilities, and our weights might explode or become too large, and computers never like that the floating point numbers become too extreme. So also that is not ideal. So what happens? Well, the key thing here that can occur is that our activation values, as we go over our layers from left to right, that they will start to blow up. It's also not ideal. Why? Well, because let's say that we are just doing a linear operation of dense layers, so no activation function whatsoever. And what that boils down to is that we're basically doing a matrix multiplication of the weight matrices. And we start something that we initialize from a normal distribution on the left-hand side, right, for a weight matrix, and now we stack matrix multiplications on top of each other. What you see then is that this will blow up. It's not because you start from a weights matrix that is initialized from a standard normal distribution that you then will end up with something that is well behaved if you then continue to multiply by weight matrices initialized from the same distribution following that. Instead, how you would like to initialize your weights, instead of this, is what you would like to, or what you would expect to see, is whatever the layer that you look at, when you take the outputs or the activations of that layer, you would like them to be well behaved and well normalized, so to have a standard deviation of 1. Meaning that it's not really the weights that you put in that layer that should have a standard deviation of 1. You should basically rescale, if you utilize a Gaussian sampling of the weights, you should rescale depending on the layer that you're in, so that the weights themselves are smaller, But after having been applied on a result of a subsequent sequence of layers of matrix multiplications, that the output of that layer that you get is something that is then well behaved with a standard deviation of 1. Basically, the idea or the key insight here was you can't just take a Gaussian sample with a standard deviation of 1 for all of the weights in your neural network. It kind of depends on where you are in your network. And if you're later in your network, you probably want to start with weights that are closer to 0, right? And there have been a couple of adaptations then to change that initialization, and they basically boil down to, well, how should you rescale the standard deviation if you perform a Gaussian sampling? The idea is nothing else than that, and depending on which activation function that you're using, this can look a little bit differently, but also here, simple idea, but had a large impact on how well behaved these networks then are. The fact that they can be adapted to multi-class and multi-output, I had already mentioned. It depends on what you stick in your output layer. Softmax, K output neurons are typically used with a softmax so that your outputs sum to 1. You see the formula of a softmax there. A bit of a strange name. Normalized exponential function would be a better name. It's a smooth approximation to the argmax function, not a max function. The hidden layers can use different activation functions. Does that mean that softmax is the only one that you can utilize when you work with multi-class problems? No, there are other alternatives as well. This is simply what people utilize the most, but it's certainly not the only one that you can utilize. Loss functions. Also, this depends a little bit on the task that you have. If you have regression tasks, then you can use mean squared error or mean absolute error. If you have a classification task, you could do the same thing. Or you can utilize categorical cross entropy or binary cross entropy. You have lots of more fancy loss functions as well. For instance, if you would work in a setting where there is a lot of class imbalance that occurs, right? Previously we said, well, you need to do oversampling or downsampling. Here too, just as is the case with XGBoost and models where you can play with the loss function directly, here too you will typically not utilize oversampling or downsampling or work on the data level. You will more likely adapt your loss function to be more in line with those imbalance concerns that you have, right? And you will use something like focal loss or things like that. So again, it can end up mattering which loss function that you optimize for, and whether you have an L1 concern or an L2 concern. It's basically, again, the same question of, would you rather have one mispredicted instance but where you're way off from the target value, or would you prefer to have 10 mispredicted instances but you're all still a little bit closer to the target value? Like, do we square that or not? Is it L1, is it L2? Yeah, that changes in terms of, or that differs in terms of which loss function that you want to utilize. So that's also something that you can play with. An interesting one to know about is, again, if you have an imbalanced data set, you can use a version of the balanced cross-entropy loss, very comparable to balanced accuracy as we saw it in the evaluation session. What is relatively interesting is this idea of focal loss, which says if you have an instance that you're calculating the loss for, and typically with binary cross entropy, you end up with a line that looks like the blue line on the top. And let's say that you're looking at an instance that has a positive class. So what we would like the network to do at the end is to predict a value of 1, right? We have a sigmoid activation function at the end, so the best that it can do is to predict an output of 1. But notice what happens if it's not predicting 1, but it's predicting 0.8. There is still some loss that you accrue from this instance, right? There is still a 0.2 difference here between 0.8 and the correct value of 1, so there is still a little bit of loss that you get. Now, if you think about, you have 20 instances, or you have like a majority class, where you're already very close to the desired value of, let's say that 1 is my majority class here, and you have 1 million of 1s, and my network is predicting 0.8. I have a lot of them. So it's very easy for the network to get some free loss benefit, to get rid of some of its loss, by pushing this 0.8 further to the 1. Are you really interested in that difference anymore at that point? No, right? What you would prefer is say, yeah, but for these few instances that I have that are 0, right, I would actually like you to work more on that side of the class balance, right? Or even in the case where you do not have class imbalance, Also there you would kind of more prefer to say, well, if I could choose, rather than pushing 10 instances to go from 0.8 to 0.9, I would like you to push this one instance from 0.4 to 0.5, right, if it's a true one. What focal loss does is it basically pushes this normal categorical entropy loss curve, the blue one, down. And what it basically says is, okay, if you have a true class of 1, and in the extreme case of the green curve over here, you can see that pretty well. What it's saying is, from the moment you predict 0.6 or higher, you already don't have any loss anymore. For me, you're already close enough to 1 at that point. Right? So this can be an interesting loss function to utilize if you work with, if you have hard instances that are kind of being ignored because your model is focusing too much on the easy instances, or because you have class imbalance. Gradient descent variance, I already mentioned the difference between stochastic gradient descent and gradient descent. The difference is basically when do you perform a weight update. With normal gradient descent, you calculate your loss for your complete training data, you average that loss, and you move your weights based on that average loss value. With stochastic gradient descent, you perform a weight update after every instance. Benefit, you use your data more effectively, but your optimization path can end up looking a little bit more like a drunk walk towards the minimum, because you're more sensitive to particular outputs over particular instances, whether the gradient descent is a more averaged kind of optimization that happens. What do most implementations then do? They go for something in the middle, right? They will say, well, we're not going to calculate our loss instance by instance or over the whole training data, but we'll work with mini batches. So don't calculate the average loss over the complete training data, but just work with sets of 64 or 32 or 128 instances instead, right? And that's why very often you need to set your mini batch size when you implement your training loop, when you're programming your neural network, or you're training your neural network. Is the mini batch size itself a hyperparameter? Yes and no. In the beginning, people thought that also how you set your mini batch could lead to networks being giving a better result or a worse result, or that there was some regularization effect that you could get by setting the mini batch size differently, and so on. The key answer is that for any mini batch size that you set, if you're then free to change the other hyperparameters of your network, you will always find a configuration that brings you to the same best performing outcome. The number of epochs that it takes you to get there, that might change. It might take you some more time, right? But in terms of performance, you will get to the same outcome. What is a bit tricky is that the values for the other hyperparameters might change if you change the mini batch size. So let's say you're working with L2 regularization, and you have just tuned the strength of the regularization given a certain mini batch size, and then you change the mini batch size because you want to speed up training a little bit, or because your GPU can't handle it, so you want to lower the mini batch size a bit, then you suddenly find that the network is not performing as well anymore, and you think, that's strange, means the mini batch size must be important. No, means that you need to retune the value of your regularization strength again, right? So typically, first pick a good mini batch size, and typically people will pick the highest size that fits in GPU, and they will pick a power of 2 and then start tuning everything else. Backpropagation, have there been alternatives for this? Well, I already mentioned this, yes. Both alternatives that use the second partial derivative as well, so which are Hessian based, other genetic algorithm based, other derivative free methods as well. People have gone or have came up with crazy things and have said, well, what if we don't train the weights at all? What if we just initialize every weight to be either 0, 1, or -1? And then the thing we optimize is not the weights, but the thing we optimize is the architecture, the topology of the neural network. Can't you then find solutions which work well? And indeed, it also exists, right? Now, these are all fun research ideas and research experiments. There are some interesting links with neurocomputing because our brain does not utilize backpropagation either. In practice, however, if you would work on a large language model, you're going to utilize backpropagation to train them, basically. Even if you use backpropagation and you use stochastic gradient descent as your optimization technique, you can wonder about whether this is the best approach to utilize. And this is the question that was just asked, because what you feel is, okay, I'm setting a step forward, and the size of my step is related or proportional to the steepness that I observe for each of my weights. But if you think about it, maybe taking a look at the history of the steps that I took and how they impacted my loss function would be a good idea as well, right? Because if I'm going down pretty steeply on my loss function, and I've just took a step that brought me from here to here, probably what you feel is, I'm still kind of going rapidly rolling down this hill. Maybe the next step that I take, I'm still going generally in the same direction as I was going before. The next step that I take can be higher, right? Until I feel that I'm kind of slowing down, and then I maybe should reduce my step size a bit. So I'm implementing a form of momentum in that case. And momentum, you can think of something that makes the step size itself also a bit more dynamic over the different rounds of training, over the different mini batches, right? If you're going down and you continue going down in the same direction, why not speed up a little bit? And if the direction changes, why not slow down a bit, right? And the second question that you can then ask is, well, should this proportionality, should this step size be the same for every weight? Why not introduce a different learning rate for each of the weights separately instead, right? And then you keep track of as many learning rates as you have weights in your network. And it's these two ideas that have been adopted by techniques or by alternate, or you could call them variants of stochastic gradient descent, such as RMS-prop, such as ADAGRAD, such as ADAM, such as ADAM-W. ADAM-W nowadays is, we could say, the most popular kind of optimization technique out there. It's a variant of ADAM which implements some fixes to work better in the case where you use regularization. It comes with 4 hyperparameters that impact like how strong momentum should play a role, and these different learning rates should be updated. It comes with an initial learning rate, so all of these optimizers will still have to start with an initial learning rate as well, probably one for all the weights or an initial learning rate for all of the weights, right? So you still need to set them, which is still something that you might need to tune. So depending on how good your optimizer is, it might also be less or more sensitive to you tuning that initial learning rate, even if it has some adaptive form of learning rate changes that it's making. ADAM-W does pretty good on all of these things, to such an extent that people have some folklore that they think, okay, with ADAM-W you can just keep all the hyperparameters to their defaults. You can keep the learning rate to its initially suggested value of, what is it, 0.001 or 0001, and then it will work itself out fine, which is the case in the majority of settings, which is not to say that in some cases starting from a different initial learning rate might be beneficial. Secondarily, even although your optimizer has a built-in adaptive approach for that learning rate, sometimes stepping in and you still adjusting the learning rate manually after a couple of epochs of training might also not be always a bad idea either. Key thing is inspect your loss curves, and inspect your loss curves over epochs of training for both the training loss and the validation loss that you see, right? So typically you keep track of a train set and a validation set. And the curve that you kind of expect to see is the red one. If you reach a plateau, then maybe it's time to reduce your learning rate. If you're converging too slowly, then maybe it's time to increase your learning rate. If you're kind of blowing up, well, then in that case you have too high of a learning rate. And same here, if your validation loss starts to increase, but your validation, but your train loss is still going down, then you're probably overfitting. Just as what we saw, like for the case of a decision tree, for instance, same concepts here. People have come up with also schedules that suggest how you should change the learning rate over the different iterations of training, from like cyclical approaches to one cycle based approaches and so on. Both Keras and PyTorch and also other libraries implement ways how you can utilize callbacks to keep track or monitor the training process and change the learning rate when necessary. And something which is commonly done is to keep track of the validation loss And as long as it keeps improving, just continue forwards. If you see that 5 epochs, it's not improving anymore, then go back 5 steps, right? Reduce the learning rate and try to continue training for a little bit further. And the whole idea is that you hope that you have found some minimum point of your loss landscape, but you're maybe kind of bouncing around a little bit. So by changing that learning rate, you're trying to find the absolute minimal point and trying to squeeze out a little bit more out of there.
Regarding the momentum strategy there, it seems to me a little bit like trust region method.
A little bit, yeah, indeed, it's very similar. Yeah, and
So trust region methods are implied as well.
yeah, yeah, indeed, yeah, it's a good comparison, indeed. Speaking of, I hope it's the, well, yeah. Speaking of initial learning rate, there have been, of course, the dream is that you can come up with an optimization technique where the setting of an initial learning rate does not matter at all anymore, or you do not even have this concept of a learning rate anymore, which is a bit harder because as long as you're not using like second partial derivatives, that will be generally hard to do. Facebook has done some research, like learning rate, free learning by de-adaptation. It never really, in some particular cases, these alternative techniques show good results, but they don't seem to be viable for every sort of model or every sort of data set. So to be honest, Adam W still seems to reign supreme in the space of the optimizers for now. When I talk about the loss landscape and the minima, and the local minima, very often people also question, but these local minima, the fact that you can get stuck there, it's a bit of a pity. It means that this technique is rather greedy. It does not find for you like the global minimum for these values of your weights. So isn't that a bit of a pity, and can we avoid that? There are a couple of things to keep in mind there. The thing is that the problem of us getting stuck in a local minimum, that's quite okay. Actually, in toy examples where we show functions with 1 weight or loss landscapes with 2 weights, you might think that this is kind of a large problem. But imagine what your loss landscape looks like if you have something very high dimensional, like 80 million weights. It's probably easier to escape out of your local minima if you have to. You have multiple pathways to escape out of that. Secondarily, people have done some analyses of loss landscapes of networks, and what they find is, yes, indeed, there are a lot of local minima. These things are not smooth at all, but typically what you see is that they all come with generally the same loss values anyway. So it's not that much of an issue that you end up getting stuck in a local minimum, as long as you do find a local minimum. Next, what people have also kind of wondered about is, well, what's ideal? If all of the values of your loss function are similar, no matter the local minimum that you end up with, or they're comparable at least, then maybe it's not so much about the value of the loss, but more like the characteristic of the local minimum that you end up in. And here, if I have the choice to end up over here or over here, I would probably prefer to end up over here, right? Because I have something that is a bit more regularized in that space, a bit more well-behaved. And again, in 1 weight, it's easy to show this, but then think about, okay, this regularization help to find positions in this loss landscape that are more well-behaved or plateauish or less sensitive to small changes to your weights, because that's basically what you're asking, right? Than if you don't use regularization. Most importantly, the problem is not so much for optimizers that they need to escape local minima and so on. The problem is mainly saddle points, as you see there. If you do not use any form of momentum or whatsoever, and you would end up in this position with normal SGD, you're stuck. You stop. No matter if you come rolling off the hill, right, and you have done a couple of steps, if this is where you end up at with SGD, it's done. You have found a local minimum. And the reason being is that you have your 2 weights. With respect to this weight, your slope is 0. I know it doesn't look like it's 0 because you know, but if you put a little step forward, it's not 0. Yeah, but in that exact spot, the first partial derivative is 0. And with respect to the other weight, it's also 0. Yeah, but if you just take a little bit step, but you take the first partial derivative, it's 0 in both directions. So you stop moving. If you use momentum, you wouldn't have that problem because you already have been moving for a bit, right? And so even if your first partial derivative is 0 in both directions, you will still try to take a bit of a step because you didn't slow down completely yet, right? And you will escape this saddle point. It's mainly these things that cause issues when training neural networks, because with your 80 million weights, there are probably a lot of saddle points, not for all of the weights at the same point, but some of your weights might die out because they have reached the saddle point. And it's mainly this that these optimizers are actually avoiding compared to when using SGD. So here you can see some references if you want to learn a bit more about those. Overfitting then, already briefly mentioned. So if you keep track of your loss on your training data and on a validation piece of data, same as with decision trees, at some point, if you have a network which is large enough, you will start to overfit your training data. And that's in fact what you expect. In such a sense that when you really get stuck in terms of knowing how large should my architecture be, or do I have a bug in my network, a very simple self-check that you can do is, first of all, make your network larger than it needs to be. And first of all, before you start worrying about generalization or test set results or validation set values or whatever, prove that you can get at least your training loss close to 0. If that doesn't work, even if you make the architecture larger, you have some bug somewhere, right? And in a lot of cases, what the bug can end up being is that you forgot to normalize or standardize your input features, because neural networks are also heavily sensitive to that. Think a little bit about why they're sensitive to that, why it matters so much for them. And probably the answer will again lie in how these weights are initialized and what they assume in terms of being well behaved for the activation values and then influencing the gradients that you end up with, right? So if you get again, if you already have an input layer that is not nicely scaled, you're basically already blowing up the activation values of that input layer, and hence probably you will end up with gradients that move your weights all over the place, right? And will hence negatively impact the optimization procedure that's going on there. Now, once then you have an architecture that can bring your training close to 0, you're probably not going to be happy with your validation loss. So what do you do then? Well, a couple of things that you can do is get more data, but that's of course an easy answer, right? That will typically not be the feasible one. Make your network smaller, but that's also not something that deep learners like to do. Apply regularization is then commonly done, so both L1 or L2 regularization, similar as what we saw previously. Other things, batch normalization can help a little bit, but it's not necessarily something that prevents overfitting by itself. But again, here, the thing that AlexNet introduced was dropout. And we'll see dropout in a second, or maybe next week, what that means. But at the basic notion, and dropout is especially something which will be important for the dense layers. Those are the only type of layers that we have seen so far. We didn't see any other type of layer yet. But for layers that are fully connected, well, why? Because there you have a lot of weights. So a lot of opportunity to have overfitting from going on. And what dropout will do is, every mini batch of training, they will, as the name suggests, drop out a randomly taken subset of neurons in that layer, and will not have them participate in the weight updates for that mini batch. And that will basically force the network to learn redundant pathways to learn the same patterns, and hence focus more on the general structure and patterns in the data rather than being sensitive to noise and overfitting on noise. We'll come back to dropout in a second. So this is it, and this already kind of illustrates that for a simple network where you're only using MLP layers, that we can tune the learning rate, we can tune the number of units, we can tune the number of layers, we can play with the loss function, we can play with the activation functions, we can apply regularization, we can apply dropout, we can, and so on and so on and so on. Right? This will stay once we introduce other types of units as well. So sometimes people think that, once you have 200 layers, and once you work with convolutional units, then this is not necessary anymore. It's still necessary to also keep in mind these basic hyperparameters as well. And don't forget to standardize or normalize your input layer. So yeah, again, deep, as mentioned. So the next question will then be, okay, we have just seen this simple perceptron, and if you have 8 of them, and you stick them in a layer, then okay, you have a fully connected layer. And if you have multiple of these layers, you have something which is deeper and something which is then a fully connected deep neural network. So what are the other types that we can come up with? And depending on the data that you look at, other types of neurons that we will discuss will be convolutional neurons, so hence will allow us to build convolutional neural networks. We'll also take a look at, in the same chapter, how we can utilize these models to move more from the classification or the discrimination task towards the generative type of tasks, because everybody today is talking about generative AI. So what does that mean, right? So discriminatory, we know you have an instance and you try to classify it into a bunch of classes, but how do you go from this and then make it more generative? It's an interesting question. Later on, we'll come back to deep learning, but then we'll see how it can be applied in the domain of text mining. So then that's when we will take the opportunity to talk about representation learning. We'll take the opportunity to talk about recurrent neural networks. And there it's also the point where we'll discuss transformers to see like how things like ChatGPT or GPT models work. Graph neural networks, when we discuss graph mining, but that will be rather brief, more as a general kind of idea what these things are, rather than fully in depth. So we'll focus more on these guys that you see there. So at least to introduce kind of the second assignment, let's at least look at the basics of the convolutional architecture and what this changes compared to the standard perceptron as we have just seen it. So now we're going to introduce basically a new type of neuron. If we go back to this example of these handwritten digits that we had previously, the number 5 in black and white, if you try to approach that with an MLP and you pick a good optimizer and you apply some dropout perhaps, or you regularize, you will get a good result. On the other hand, you work with very small images, 28 by 28 pixels. They're black and white images, and you only have 10 classes, right? Secondly, all of the images in your training data, if you look at them, they have already been well prepared for you. If you look at the images in the MNIST dataset, as it's called, you will see that all of them take like the same kind of volume of the 28 by 28 pixels. They're nice in the center. They're not rotated. There is no background noise present, right? So they have already been cleaned up for you. Imagine that you would then apply your MLP network in the real world, where you would implement this on a smartphone device, right? And tomorrow a user would come along and they draw the number 5 like this because they're holding their screen sideways. Would your network still know what to do with this? No. Not in the case of an MLP. Or they draw the number 5 in a tiny way in the right-hand corner, also not. Maybe you can think of some pre-processing steps that you could then also apply on these new test images, right? But again, this kind of shows you that be careful when working with a data set. Think about what's your real-life context going to be. What are your unseen images going to be really, right? Or am I going to extrapolate from my training data, or is this something that's already been prepared in some way? Now, what's the problem with this? We can then at least think, okay, how can we make this smarter? It's a bit of a pity that going from here to here, that we lose kind of already predictive power of our MLP. And the reason is because, of course, at every unit, I added in the layer that followed it, that this was fully connected to all of the pixels, in this case, of the input layer. So it's basically, well, if you have a number 5 that would be able to show up in this position, or in this position, or in this position, or in this position, that you would probably have different units having to focus on different spatial locations in the input, right? So this is not positionally independent. In the case of a fully connected neural network, you're kind of spatially dependent on the input. That's a bit of a pity. Because if you look at images, you can ask the question, yeah, but it's not so much the location of where something is in the image that plays a role, right? If I'm trying to build a network that needs to detect whether there is a dog in the image or not, or a cat, I'm not really interested, I might be, but for that type of classification, I'm not necessarily interested to know where that dog is in the image. And it doesn't matter to me so much that the dog is here or here or here or here. I would like to have something that can get excited by there being a dog, no matter where the dog is. Problem number 2 is tomorrow, if I want to give this network an image which is not 28 by 28 pixels, but which is 70 by 70 pixels, would that work? No, right? Because this thing has exactly as many weights as there was weights in my input image, 784, right? If I make this image larger, it will not flow through these operations anymore. The only thing I can do is rescale the image first somehow, which is also a pity, right? Again, it highlights the spatial dependence that a fully connected neural network has. So if I try this out on ImageNet with my 1,000 classes, color images, I could still utilize an MLP, but I will have a lot of weights to train and this thing would blow up, right? So isn't there a smarter approach? And it's exactly what CNN and what AlexNet introduced. They utilize, apart from using a GPU and ReLU and dropout, they also utilize a convolutional stack in terms of their architecture. Okay, what does it look like? AlexNet, the example or the architecture is shown on the slide. This is kind of the first iteration. Later, there have been adaptations that are made of this architecture as well that we'll take a look at, but this is kind of a good starting point for us to kind of understand what the whole deal was with AlexNet when it came out. Input is still a matrix of pixels. Okay. If you have or if you have black and white images, then this is just a matrix with a width and a height, like we did before. 0 for black, 1 for white, 0.5 for gray, that's it. Damn, we have color images, not black and white. And what do we do? Well, you know from computer graphics, if you open up a picture in Paint and you want to change one of the pixels in there, that you can choose your red, green, and blue values, right? So that's something that we could do. Right, so you have for each image, you have your red channel, your blue channel, and your green channel. And if you shine light through these 3 colors and you combine them, then you can get everything between white and black in all the different colors of the rainbow, right? So you can just take those values and use them as an input. Does it have to be these values? Can it be HSV, U saturation, and what's the other one? A brightness, right, as well? Yeah, sure. Could you use print values, CMYK? Then you have 4 values. Yeah, sure. This is just a choice, right? Because it matches with how most of our images are stored or represented on a computer anyway. So then you have an input layer that is not a matrix, but is a cube with a width, height, and 3 channels, a depth of 3. Because for every pixel, for every position in your 2-dimensional map, you have a vector of 3 values, a depth of 3. Then you see that you have both convolutional layers, and you have like these triangle things, or here, these max pooling things in the middle. And then at the very end, there is something we already know. So actually, the very last layers, that's something that we already know. Dense, dense, dense. We have seen that name previously, right? So these yellow blocks over here is something that actually we don't need to explain anymore. These are just fully connected layers. One with 4,096 neurons, another one with 4,096 neurons, and one with 1,000 neurons at the end. Why 1,000? Because we have 1,000 classes. Softmax for the last one, ReLU and ReLU for these 2. So, okay. So the most important unit and layer to learn about is the convolutional unit. And we will take a look at the 2D conv unit. There exists a 1D and a 3D version as well. I will explain to you why this is the 2D version. A convolutional unit learns a kernel for its weights. So its weights themselves, so now this thing does not have as many weights as inputs that it is connected to. It learns a matrix of weights. The size of this matrix is user configurable. Now I can tell this unit, no, you learn a 2 by 2 or you learn a 3 by 3. That's the size of the kernel, that's the size of the filter. So now weight or number of weights, irrespective of the inputs that this thing is connected to or receives, the weights are user configurable. Right? For a perceptron that was different, that was dependent on the number of units that I had in the layer before. every unit expects, or hence this is what makes it a 2D convolutional unit. As an input, this expects to take in something that has a width times height times a certain depth. So if I apply a unit on my input image directly, my depth is 3 because I had 3 channels for red, green, and blue. It will use these weights that it will learn through stochastic gradient descent to produce me, if I then apply this and I look at its output, the output of this thing is no longer, as was the case with a perceptron, is no longer a single number, but is a 2D matrix of numbers. This is what makes it 2D. Right? Because it's applied on a 2D times depth input, and it produces a 2D output. How? Well, as the slide suggests, it will also apply a sum of products, like the normal perceptron. It does the same thing, but it does so by taking this filter, this kernel, with a fixed size, and sliding it over my input image, which is this width times height thing, from the top left, and I'm moving 1 pixel to the right and down until I have reached the bottom right. For every overlaying position, right, so these are my black and white pixel values, and this is the filter that I'm using, and I'm starting in the top left, so I do 1 times 1 plus 1 times 0 plus 1 times 1 plus 0 times 0 plus 1 times 1 and so forth is 4. Sometimes they also apply here too, for every value that I'm calculating like this, an additional activation function as well. So we could take this value and squeeze it through a ReLU, right? And then, yeah, in this case, the result would stay 4 because 4 through a ReLU is 4. Move 1 to the right, I do the same thing. So I do this, and this is what generates my output map. A couple of observations. Here it's simple because my input did not have a depth of 3, but my input has a depth of 1. If you have a depth of 3, then how do you do this sliding? Not clear yet. My output is smaller than my input. I start with an input which is a 5 by 5, but I get an output which is a 3 by 3, right? If you don't want that, we can apply padding around the edges of the image so that we can basically move outside of the boundaries of this thing, right? And make sure that the output is the same size as the input in terms of width and height. For instance, by just pretending that there are like zeros around that image and just doing it that way. The same kernel is used over all positions in the image, so no matter where I am, I'm applying the same weight values, so I'm doing a form of weight sharing there as well. Do you always have to move 1 pixel to the right and to the bottom? No, sometimes you can move 2 pixels as well. That's called the stride, by how many pixels you move right and downwards. Typically, you keep that to 1. Thing that you can also pick, apart from the stride, is the size of the filter. Here it's a 3 by 3, could be a 2 by 2. If you have an input which is not of a depth 1, but has a depth of 3, for instance, or a depth of d, or n, then what changes? We are still going to take this filter, and we're going to move it from the top left to the bottom right, going right and going downwards. My filter here was a 3 by 3. You could say, well, okay, that means that you apply this 3 by 3 filter for the first slice of your image, but you also do that for the second slice of your image and also for the third slice of your image. But that doesn't make a lot of sense, right? Typically, like the same thing that would look at a red channel would not work on a green channel or on a blue channel. So in this case, you can still say that your filter should be a 3 by 3 or a 2 by 2. But your filter itself will have a depth equal to the depth that it received as an input. How does it produce its output? Well, now because I have a 3 by 3 by 3, in this case, kernel, again, I overlay this kernel on the top left position. I take the sum of products here, I take the sum of products here, I take the sum of products here, then I take another sum to produce the final output result. So the output, irrespective of the depth that this unit works on in the input side, the output of a single unit is still going to be a two-dimensional thing, right? But that's just one unit. So how would I have a network where I stack multiple such operations on top of each other? What happens if I now do not have a single unit like this, but I create a whole layer of them? Well, then we get the following. I start with an image, and let's say it's a color image, width, height, a depth of 3. So W. Now I know that I can connect a unit to here, and this unit will have a weight dimensionality which is equal to a user-specified width and height, right? Which is not the same as the image. This is like before we used like a 3 by 3. So that's what I can pick. Times depth of the kernel, 3. This being equal, there I don't have a choice. That's why I can't specify it. The output that this thing produces will be a two-dimensional thing with something that's more or less similar to the height of the input that it received and more or less similar to the width of the input that it received. Why more or less? Depends if I use padding or not. If I don't use padding, this will get smaller. If I do use padding, I can actually guarantee that I can keep the same height and width. Now I will make a layer of these things. So I don't have a single unit like this, but I have a couple of them. N convolutional units that will each learn their own 3 by 3 by 3 kernel. So if I ask for the output for all of these, they will all give me an output map that they produce of a height and a width. How can I now add in another layer with maybe M units on top of this? Well, you see, hopefully you start to see, if I now would just simply take these N output maps that I have and I stack them on top of each other, what's the shape of the tensor that I get? H times W times N, because as many units as you had in this layer, right? That will be the depth of this output thing that you generate there. And now, because you have a depth again, you can stack in another layer of convolutional units on top of this. And these will learn, again, 3 by 3 by N kernels, and they will produce a shape of H times W times M, as many because we stack their output maps again. And hence I can keep stacking layers on top of each other like this. Right? So that's why this works. Okay, that's how a convolutional unit works. Problem is that, well, if you make this quite deep, and especially if you use padding, so you keep the same H and W as you go across your layers, yeah, that might be a bit annoying still to calculate. So computationally speaking, maybe from time to time it makes sense that we apply some sort of downsampling, and that's called pooling. Basically a resize. So this thing does not have weights, does not have learnable parameters. This thing is just there to say, you know what? Before you go to the next layer of convolutional units, you have this H times W times N thing over there. It's a bit too large, so let's resize this into H over 2 times W over 2 times N. Just do a resize of these N maps that I have first. How that resize and actually goes, well, you have some choices. You can do max pooling, where you retain the maximal value in each window that you slide over. You can do an average pooling, basically different resize mechanisms. But no matter the one that you pick, these things do not learn weights. So they're just there to perform a resize operation. An extreme form of pooling is global average pooling, where you say, well, in the case where I resize like this, I'm basically resizing all of the output maps that you get to not have an H times W, but to basically resize them to be, let's say, half as small. Right? I can do that by looking at the average value for each quadrant, or I can do that by looking at the maximal value of each quadrant, or the minimal value, or the median value, whatever. If I take an extreme form where I say, you know what, just pick the average of all of the values in this output map. There's like doing some sort of extreme form of your resize where you're basically converting this 2D output map to a single number. If you apply this on a layer like this, you lose your first 2 dimensions, and you basically just get a vector of size m. Why is this sometimes done? Well, it says here sometimes you utilize this as an alternative or as a way to make the fully convoluted or the fully connected layers work better. The idea here of using a global average pooling is not so often in the intermediate layers, but is right at the end, maybe before giving this to a fully connected dense layer. And why is that? Well, if you would not utilize this, then the last inputs that we would have, that we would give to our dense layers, would still be something that has 3 dimensions, that has a certain height and a certain width and a certain depth. And maybe we have made the height and the width by then very small, could be, right? But we still have a certain height and a certain width and a certain depth. Maybe we have not used any pooling at all so far, and we have used padding so that the height and the width are exactly the same as the height and the width that we received on the input side. Problem, if we now say let's connect a dense layer of 8 units to this, then the number of weights that this thing needs will be, well, yeah, 8 times h times w times m, because every perceptron in here will be connected to every kind of position in this cube in there. But that means that you get a fixed number of weights, meaning that, well, now your h and your w are becoming kind of a constant, meaning that on the input side, every instance that you give needs to be of the exact same height and width. And that's why sometimes you will read or you will see, if you use a convolutional neural network, you first need to make sure that all of your images have the same height and width. You can't change that. The reason why not is because then you would break up the kind of assumed values of h and w there. Now, the trick of global average pooling is, well, if you then first average these dimensions out so that you get a vector of size m over here, then no matter what your starting h and w were here at the beginning, it doesn't matter because here you just convert them to a vector of size m anyway. And then if you add a fully connected network on top of this, this m stays the same, your height and weight do not matter anymore. That's basically it to make a convolutional neural network. And do not be afraid in Keras, this is expressed pretty easily. This is what you see here, right? It basically says, well, I want a sequential model. My first layer consists of 16 2D convolutional units with a 3x3 kernel, and I want you to use padding and the ReLU activation function. And then another layer of 16 2D convolutional units. And then I want some pooling. Then I flatten everything out, and that's the reason why I need to flatten is because I'm not using global average pooling. So we are kind of in the situation where my last output will be an h times a width times a depth, right? And the depth will be 16 because I just saw that I'm making 16 units at the previous depth, right? And I could figure out the height and the width, right, as well. But I first need to flatten this out to be able to connect it to a dense layer, otherwise Keras will complain. Otherwise Keras will say, hey, you're adding in a dense layer, but the input that you give me here is something three-dimensional. Okay, fine, first flatten it out. And then another dense layer with the last one just having the same number of classes than the ones that you want to predict, and you use a softmax activation function there. What's the difference then to a fully connected neural network? So let's recap. This is the simple fully connected case. Yeah, question? If you use global average pooling, yeah. Correct, but yeah, that's actually a good question. But then, at least for the input, the way how the 2D units work, they basically don't care what the shape of your initial input is. Their output map that they produce, you can apply that operation on whatever sized matrix that you would give in with RGB values, and they will produce you an equivalently sized output. So indeed, normally how we've been drawing this, we have been kind of saying, but you need to know the number of input units that you have. In this case, you can leave that open. You can leave that free until the usage of your network. Because in order for the 2D unit to be defined and to produce its operation, it does not need to know the exact input because it slides over the thing, no matter how much size it has, right? So that's why that works. Yeah, yeah. So here, because you have a fixed number of weights for each perceptron, your input needs to be fixed, basically. That's the thing that you can see there as well. So this is the fully connected setup. 2 layers, hidden layers, and 1 final layer with the outputs. Does this work? Well, yeah, I hope so, or this will produce something, but you see in this case, it doesn't give me a perfect output result, right? So every line here corresponds with a weight. It's trying to do something, but probably my drawing is not nice enough, right? So I can maybe try another one here, like the number 8. Yeah, well, yeah, look, this one is doing better, right? So it likes my number 8, but again, like what I discussed before, if you would do some trickery like this, it's already a 7 and things like that. So here you end up with a lot of weights and for not that much predictive power. This is the convolutional neural network variant. I'm going to first hide everything except this first layer of convolutional units. My input layer is the same. I just have pixels by pixel values. Activation values are shown in the little blocks. The more bright it is, the higher the activation value is. Right? So white here corresponds to 1, black to 0. The outputs that you see here, observe that these now look like 2-dimensional outputs. These are the output maps that each unit has produced after having done its operation on this input. To do this, if I then take a look at one of these units, you see that no matter where I am in this output map, it's applying the same weights. The colors of the lines that you see moving here do not change. So this is the operation where it just slides from left to the right-hand side, from top to bottom, to produce its output map. Now, if you look, at least for this first layer, you can kind of at least guess better than what we could before. What is it that these things like to see? No matter where it is in the image, what is this kernel picking up on? If you'd have to take a guess, I hope that you can kind of see, well, this one is getting excited. Well, they're all kind of getting excited, obviously, because we're working with black and white images. They're all kind of getting excited by edges. And this one by top and bottom edges. And this one by like another kind of direction of edges. And this one right and left edges. And this one mainly top edges. And this one mainly bottom edges, right? That already makes more sense to what we expect these filters to do. Next step is a downscaling, but you see this thing learns nothing. It just resizes the image. The next step is that we do a convolutional layer again. And now, because in the very first image we did not have a depth, so the kernel here is a 3 by, or is it a 5 by 5? Yeah, it's a 5 by 5 by 1, because the depth of my input here is 1. In this layer, I'm working with kernels that are 5 by 5 times depth of the input that they work on, which was 6, right? Because the previous layer produced 6 output maps that are stacked on top of each other, which is why here you see connections going for each of these blocks to all of the input slices, right? And then basically you just create a stack like this, and at the end they don't use global average pooling. So here you can see that indeed in this fully connected layer we do have weights, as many weights as we have values in the output of the previous layer. If we would have done global average pooling, we would first have averaged all of these little outputs down to a singular value, right? Here we're not doing that. This is simple AlexNet version, right? So fully connected, fully connected, fully connected. And here is typically the place where during training we would have to use dropout to avoid overfitting. That's not shown here, but that's what's been done. And you see prediction much better. So that's the convolutional architecture. Again, watch the 3 blue 1 brown video, who uses a lot of nice animations if you would like to get a refresher. I know this is maybe a little bit at the same time, but it's not that hard to utilize. I have 10 minutes left. I think you guys are pretty cooked, right? And so am I. The rest we'll see next time. Before we leave, however, I will quickly introduce 5 minutes, not more than that, what I have worked up for you to work on for the assignment. So as you know, last week I was not here because I was walking through the cold, frozen mountain area of Iceland, starting from the University of Reykjavik, and then having made a terrible mistake to do a small tour there, and yeah, it's still snowing. Lots of volcano activity, so very barren landscapes. There are no trees there, which make it quite special. And while I was walking around there, I was wondering if I would take a random photo here from the mountains from a road in Iceland and compare it to a random picture that you take from a mountain area somewhere in Austria, I would probably be able to tell the difference, right? And this reminded me of people who competitively play the game of GeoGuessr, which you maybe might have seen, like these crazy people on TikTok who just look at a Google Street View image and they go, oh yeah, we're in Peru, right? So I thought, well, if they can do that, why can't a neural network do that as well? So I've collected a data set with about 10 different locations, all mountainous areas, and launched some OpenStreetMap queries where I said, give me a random mountain which is higher than so many meters. In a zone around that, place me somewhere on a road, and then scrape using Google Street View, open web browser, and look around and scrape me the panoramic picture from there. So 10 locations, more or less, 60 pictures per location, more or less. Your job, see if you can get some predictive accuracy out of there. So that will be your task. If you want to be a bit more fancy, you will have some kind of extra point questions, like you see that these are panoramic pictures, because it's like the full 360 view at that spot. Maybe you can utilize it in some smart way to cut it up into different like angles that you can use to maybe enrich your data set as well. If you would like to apply some data augmentation, that's maybe something that you would have to do. What you can also do is, if you'd like to utilize a pre-trained model that you fine-tune, be my guest. If you'd like to use a model that's already open and available, be my guest. So idea to approach this is your consultants. This is my question. You have like 1 month time, impress me, see if you can do something. Also extra points if you can use some kind of interpretability technique to kind of show like what is it actually looking at, to spot the differences between Austria and Iceland and so on, right? So if you find that the 10 countries are too difficult, you can reduce them down to a set of 2 and then maybe focus more on the interpretability angle, so you will have some choices that you can make along the way. Coolest thing, I will also give you the source code that I utilize to collect these images. Show me that you can apply it on a new bunch of images and that it works, basically, that you didn't overfit, because you will have to split off your own test set here as well. Would also be nice to show. Kind of get the idea? So that will be assignment 2. Information and data set will follow tonight. And yeah, other than that, continue working on assignment number 1 as well. See you next week.